Welcome to all attendees for our Eastern Pennsylvania branch of the ASM 100th year birthday celebration. At the same time, it is our 780th meeting, showing how active our branch is. I'm the EPA ASM president that will give you a brief introduction to the ASM, the National ASM, our branch of the ASM, and today's program. So the National ASM sent us this congratulations slide, and we are very honored to have at least three very important attendees from the National ASM. First, the president of the ASM, Dr. Vic Derrida, will talk to us in a few minutes, as well as the chief executive officer of the ASM, Dr. Stefano Bertuzzi, and our liaison with National ASM, Ann Dempsey, who is always reachable and helping our branch in organizing national support to us and other branches. We particularly wish to thank the ASM for its support of various activities in our branch, such as our I&I forum in December, the visiting ASM distinguished lecturers and the program, and the ASM Peggy Cotter Travel Award program for early career branch members to attend the yearly ASM microbe meeting. We had this year actually three fantastic candidate who won the award. Unfortunately, the meeting being cancelled, they couldn't travel. So why the ASM? So this is just a reminder about the benefit of the ASM. The ASM will help our community, particularly by connecting more than 30,000 of our peers, so of microbiologists. Also very important for many for students and postdoc for their career, this professional development, and also later for leadership opportunities. What I think is the most important or very active is the cutting edge science with the ASM meetings, which I like to participate, the webinars, all these virtual journal clubs. They have an ASM scientific journals. They also have books, and they have a lot of additional activities to offer. Here is a link actually to the asm.org, to the membership if you want to participate in the National ASM Society. The ASM also has now a very nice online site, which is called ASM Microbe Online. You can actually find it here, asm.org/microbe online, which has a lot of different talks on COVID-19, but much more actually on a lot of other topics, over 1,000, also with electronic posters. And it also links the industry and science programs. What I also find very interesting with this microbe online is not only this one, but also the link with the podcast, which is essentially asm.org podcast link, where you can find a lot of interactions and discussion of microbiology scientists presenting their research. So our website, our society, our branch has recently redesigned its website, which you can find at epaasm.org, which is managed by Dr. Irv Nachamkin. And it has all the info about our monthly meeting, our history, and also how to join the Eastern Pennsylvania branch of the ASM. So it's actually, it has a lot of information about how to get there if you're already an ASM member or if you are yet not an ASM member. What's really obvious is that it's not an expensive deal for full membership, only $20. Also very nicely for students, it doesn't cost. So really I suggest all the students who are listening now to join. There's a lot of student activities, and you can actually also interact with join our I&I forum, and our annual symposium to give posters or talks. It is also free for emeritus, and as I said, only $20 for full membership. Members include Delaware and South New Jersey regions, and this money is mainly used to invite outside speakers for our meetings and support student activities. Now, the current membership of our branch, we have over 500 contacts, 170 active registered renewed members. Among them are 52 students and 14 emeritus faculty. So now to the program. We'll have 5 consecutive uninterrupted talks. For our first presentation, Dr. James Pupa will tell us about the history of our branch's activities over the last century. Then we're going to have 2 20-minute talks focused on clinical microbiology, followed by another 2 20-minute talks on basic microbiology topics. These talks all relate to our branch and our geography. And I was told that no speaker has any conflict of interest disclosure to make. So that's done now. The meeting will end with a 50-minute long Q&A session here, which will be led by Dr. Toby Eisenstein and Dr. Linda Miller. To make this meeting more interactive, Zoom participants will be able to raise their virtual hands and be unmuted to ask their questions. However, written chat questions also be addressed during these 50 minutes. Now, I'd like to thank today's 5 speakers, including Dr. James Pupa for the impetus and passion he brought to make it happen. Also want to thank Doctors Linda Miller, Toby Eisenstein, Michelle Kutzler, and Alan Evangelista for planning this meeting's program. Finally, I have to thank naturally Dr. Vincent Tam for hosting us all with Zooming expertise. Next, we will greet, Okay, so we will greet Dr. Vic DiRita, who is the ASM president. Dr. DiRita is the Rudolph Hugh Endowed Chair and Department Chair at the Department of Microbiology and Molecular Genetics, Michigan State University. Dr. DiRita did his PhD at Purdue University and his postdoc at Harvard Med School with Dr. John McAlanos. He then started at the University of Michigan, where he went from assistant to full professor and moved 5 years ago to his current position at Michigan State University. Dr. DiRita has long-standing research programs understanding mechanism of virulence regulation in Vibrio cholerae. Over the year, his research expanded into Streptococcus pyogenes and mainly into Campylobacter jejuni pathogenesis, with the development of novel genetic tools for C. jejuni and chicken and ferret models of C. jejuni colonization. More recently, Dr. DiRita has been working on the antibiotic-resistant escape pathogens that are so prevalent in current healthcare settings. Dr. DiRita has trained multiple successful students and postdocs over the years, in addition to leading an NIH T32 supported training program in microbial pathogenesis for 20 years at the University of Michigan, where he served as assistant and then associate dean for graduate and postdoctoral studies at the medical school. Suffice to say that his great research program were and continue to be well funded by the NIH. So now, let's go to Dr. DiRita.
Well, thank you, Dieter. I really appreciate that generous introduction. And thank you, Vincent, for hosting us all today. You know, it's a real honor to be at the 780th event of any group. So it's just a tremendous mark of your history. You know, we've got 30,000 members at the ASM, as Dieter pointed out. And it's a privilege for me to be part of the ASM, the National ASM, and to be its president right now. And we're all over the world, and we have this tremendous mission of promoting and advancing the microbial sciences throughout the world. But it's really at the local connections where we have our greatest impact and where we really have the most fun. And branches are a place where that happens to the really the highest degree that we can achieve. And the Eastern Pennsylvania branch in particular is one that that advances that ethos of knowing one another, being colleagues, knowing who the individuals that you meet with on a monthly basis are, the types of meetings that you have to have clinical, basic research, graduate student involvement, industry, government. It all seems to be happening really in your branch, and it's just really amazing to see how the history of this how the history of your branch has really mirrored the history of our field of the microbial sciences. I had the honor of speaking at the Eastern Pennsylvania branch meeting in September of 1999 when I was an ASM branch lecturer, and I was blown away by the type of meeting that I experienced, because I had not been to a branch meeting before that, remarkably. I've been to several since, but before that I had not been to a branch meeting, and I really had no clue really what to expect. And when I came to Eastern Pennsylvania and saw what an interactive engaged group there was, and how many great scientists there were, who my papers I'd read and who I knew a little bit, it was really just impressive. And we have some very strong branches around the country, but there is definitely something very special about Eastern Pennsylvania. We hear all the time that the branch is how I got involved with the national ASM, and having that interaction and the connections in the branch really helped me get involved in the national. And as I said, we hear that a lot. I think it's true. It is demonstrably clear from the Eastern Pennsylvania branch. So many leaders in the ASM, the national ASM, so many names that we all know of came out of this region. I'm going back to David Berge, Lydia Rabinovich, Saul Goodgall, but down now to Jim Poupart, Andy Chang-Vollmer, Toby Eisenstein, Herb Nachomkin. This is a place where a lot of microbiology in the United States can find its origins, and it's exciting to see you celebrating your 100th birthday. What's impressive to me is that I know that Jim Poupart is going to talk about the 100th anniversary, and he's going to give the history of the branch. What he's going to leave out is the 40 years or more of microbiology in Philadelphia that was going on before this branch started. So really, Philadelphia and Eastern Pennsylvania have been the cradle of microbial sciences in the United States. And Jim's great book, The History of Microbiology in Philadelphia from 1880 to 2010, which is now 10 years past that, really lays that out nicely. I had asked Jeff Carr, our archivist, to give me some interesting documents and history of Eastern Pennsylvania, and it was a massive dump when I got all the information back. It was remarkable. I know that Jim's going to cover a lot about that, but from my editing, it's really exciting to see and really impressive to see how much history has emerged out of Pennsylvania. So I wish you another 100 years forward in great success. It's just been terrific to see all the great achievements that have come out of Philadelphia and Eastern Pennsylvania, the great collegiality. Mike Schmidt, when he was the head of the branches for the ASM, used to say one of the mottos that they had about ASM branches was, it's a place where everyone knows your name. And again, you really get that feeling from the Eastern Pennsylvania branch. And not only does everybody in the branch know your name, but the history of this group has been such that the rest of us know your names as well. And so congratulations on 100 years, best 100 more, and have a great meeting. Unfortunately, I'm actually on a study section right now, so I'm going to be leaving. I don't think I'm reviewing anybody's grant here, but I'm on a study section, so I'm not going to be sticking around. But I wish you a great day, and thanks again, Jim, for the opportunity to speak here. Congratulations on 100 years, and keep it going. Thank you.
Thank you.
Thank you very much, Vic.
Much, Dieter.
So I think Robbie and Linda, you can go on with presenting Jim, and we can start, I guess.
Okay. Okay. I would like to present Dr. Jim Poupard, who is going to give the first talk. I could go on for a very long time about Dr. Poupard, who obtained his PhD from the University of Pennsylvania, Director of Microbiology at Bryn Mawr Hospital, Director of Clinical Microbiology at GlaxoSmithKline. But so importantly, Jim has been a driving force in Philadelphia and in the Eastern Pennsylvania branch. He's probably been on every committee, inspired countless number of students to come to the meetings. He was certainly a branch president and has for the past number of years been our archivist. Jim is also the archivist for ASM, or has been the archivist for ASM National. If you have a question about anything historical microbiology, Jim is the person to go to. So I'm not going to take up more of his time because I'm very excited to hear his talk. And it really was Jim who said, we need to celebrate the 100th meeting about a year and a half ago. So here we are. We didn't think we'd be doing it virtual, but I'm very excited to introduce Dr. Jim Poupard.
Okay. Thank you for that introduction. And I'm very happy to be here. I'm going to try to get a little bit over 100 years condensed into a half hour. So it's always a big challenge, and I've done a lot of editing, but I'm going to do my best. The Philadelphia, before I present the highlights of our 100 years, I'd like to present a quick review of the evolution of bacteriology in Philadelphia leading up to 1920. And the reason I think that's important is because this helps us explain why our branch is so unique. So that in Philadelphia became the medical capital of the American colonies. We had the first medical school, the first hospital. We ended up having 5 medical schools, which is really significant. And it's significant in the sense that that really drove a lot of the bacteriology that followed. But some people forget we also became the pharmaceutical and vaccine capital of the United States. In order to really comprehend how bacteriology got off the ground, there's 3 elements that went into bacteriology: microscopy, hygiene, and pathology. And Philadelphia had all 3 very early. Starting in as early as 1851, we had the first, Joseph Leidy is America's first recognized mycohospist, as well as parasitologist. And in 51, he wrote A Flora and Fauna Within the Living Animals, which some people consider the beginning of the microbiome studies. In 1865, hygiene was added to the med school curriculum after the Civil War, because hygiene and the bacteriology part of it became much more important. And in 1876, we had the first series of bacteriology lectures from Dr. Tyson when he became head of pathology at Penn. So our history starts very early. In 1889, Dr. Shakespeare became the bacteriologist at Blockley Hospital, and he was the first Philadelphian to have the title of bacteriologist. And I'm going to spend a little bit of time on this laboratory of hygiene. The laboratory of hygiene was opened in 1892. And this is very significant, and it will become part of every one of our branch periods. The building was unique when it was built in the United States. It was unique because it's often compared with the Pasteur Institute, which I know is a little exaggeration, but that's because it was built exclusively as a laboratory building with all the insides geared for bacteriology labs. And the building resulted from negotiations between Penn and a rich publisher who placed a lot of conditions on the donation. It was one of the conditions was it was to be located away from the medical school to show that bacteriology is a separate entity from medicine. That's why it's on 34th Street. And the bacteriology courses there were taught by initially Abbott and then Abbott and Berge, but they not only taught the courses in the laboratory of hygiene, Abbott and Berge taught the courses at also in the medical school, the dental school, and the veterinary school very early. So again, these were all strong in bacteriology at an early age. And also in 1892, the first Philadelphia course in bacteriology by the Penn Medical Department became mandatory for third-year medical students. Now, how is that related to the laboratory of hygiene? One of the other parts of the donation was that Penn's medicine increased their med school to 3 years instead of 2 years, and bacteriology had to be mandatory for all the medical students. So this is the beginning of the laboratory of hygiene. I'm just going to take a quick note for Lydia Rabinowitz. Lydia Rabinowitz was born in Lithuania to a Jewish family, but she got her PhD in Switzerland and then became Robert Koch's assistant. And she realized in Germany, a woman's not going to get ahead. So what did she do? She came to the laboratory of hygiene in 1895 in order to negotiate with the Women's Medical College. And in 1898, she was made professor. She was a very popular teacher. She was made professor, which is probably the first woman bacteriology professor in the United States. I can't verify that completely, but it makes sense. And that it was a very controversial position because A, she was not an MD, and B, she was not a man. So Philadelphia was way ahead of the rest of the United States. There's two more branch dates that are important before we get started on the history. And one is in 1899, in December of 1899, the Society for American Bacteriologists was formed. The founders were Jordan and R. Abbott and Kahn, so we had connections through it from the very beginning. And it really showed that in 1899 is when bacteriology was established as a separate discipline of science. In 1912, we formed, the Microbiological Club was formed. Now this club is important to us. This was formed by 12 and eventually 15 members in Philadelphia who formed this club in that they met once a month. And does that sound familiar? Once a month became a tradition in Philadelphia. They met once a month to discuss what was going on in bacteriology. And it was a dinner meeting at Palumbo's in South Philadelphia. The minutes aren't too good. A lot of the minutes describe what wine was served. And there were a ton of arguments about how to do bacteriology and what was happening and what was important. So it was a very contentious group. And they even survived World War I, although a lot of them were drafted. And the reason I say this is so important is because first it demonstrates how much interest there was in bacteriology in Philadelphia. And it's also why we were not one of the first branches, since the SAB initiated branches in 1917. And we certainly had a lot of connections with them, but that since we had bacteriology meetings once a month, it wasn't really needed. It wasn't a big need to join in 1917. So to look at our history in 5 phases, the first phase, the early years, 1920 to 1935. That's when it all began in February 24th, 1920, when David Berge at his office at the Laboratory of Hygiene called the Microbiology Club together. And he also notes that he said, I invited a few extras, and those extras were pathologists, to form the Eastern Pennsylvania branch of SAB. They met on Tuesday evenings, Tuesday every month from October through May. There were, if you look at this period to 35, 20 to 35, there were 117 meetings and they averaged 4 topics per meeting. So it meant that in this period, there were, I can't see the number, 400 and something topics, which shows how important, how this alone traces the whole history of the evolution of bacteriology. And again, all these things are in our archives. So it's an amazing source. In 1925, it was moved to the 4th Tuesday of every month. And by 1925, we had approximately 25 members. If you look at the first 10 presidents, it's very interesting for several reasons, but one of the reasons is that don't look at the names, look at the institutions. You've got universities, you've got the med schools, vet school, dental school, research institutes, and pharmaceutical companies, all with our first 10 presidents. And actually, when you look at this, it reflects our presidents at the present time. If you look at the 52 presidents that we have, you can see that the percentage, 75 is still med school, university, hospitals. 12% of our presidents from pharmaceutical industry, which is another characteristic of our branch, the joint efforts we had with the pharmaceutical industry. 6% for government and 8% for other. So go to the second period, 1936 to 1940. And in that period, in 1936, Harry Morton and Dr. Boucher, Morton at Penn and Boucher at Jefferson said, look, there's a lot of real changes that are needed, that there's a lot more microbiologists more than these puffy people that are on our branch right now, because it was sort of a closed membership. So they said we need changes. So the changes were membership was open to all interested parties, which was very controversial to some of the old timers, but they said that's going to ruin the branch. And of course they were wrong. And it was moved to one location because at that time, whatever member sponsored the branch, that's where that meeting was. And in 1937, Dr. Morton started our numbering system. And we can't take full credit for that numbering system. We have to give credit to Baltimore. It was in a conversation, somebody said to Dr. Morton, well, Baltimore numbers their meetings. And he said, well, we have 10 times more meetings than Baltimore. He went back to the 1920s and calculated, and that's where we have our numbering system for the meetings. And in 1938, we had 166 members, so it was getting more complicated. So we bought an addressograph machine and penny postcards. And these are the penny postcards. This is what they look like. Now, I know we're microbiologists, but we're experts in micronizing a huge amount of information onto one penny postcard. And we have hundreds of these postcards. These postcards were used as a meeting notice for at least 20, 25 years. Anybody who wants them as a souvenir can contact me. And we go to phase 3 is World War II and the post-war. Well, World War II, in 1941, Dr. Morton said, look, the war is coming and we're thinking in terms of trench warfare, anaerobic infections. There's going to be a lot of need to train new microbiology people in field hospitals in Europe, all over the place where the military is going. So what we should do is come up with a program of visual aids, some way how to put together manuals and all for teaching them how to do anaerobic infections and things that are going to be connected with wounds and tropical diseases, et cetera. And he took that idea to National, and they had a conversation, and the National said, okay, in 1942, we formed the Committee on Material for Visual and Instructions in Microbiology with Dr. Morton in charge of it. And so he assembled a tremendous amount of teaching material that was used in World War II. And that goes back to our branch. During World War II, they also predicted we're going to need to cancel the meetings because so many people were going to get drafted and that we just couldn't keep up the tradition of monthly meetings. Well, the bottom line is there were no canceled meetings. So it comes out to a world war, and I can add even a worldwide pandemic won't inhibit the branch from having monthly meetings. And what actually happened during the war is people were drafted and sent to Philadelphia because Penn was the leader in aerosol research, and the Phipps Institute, we had so many research institutes, and our expertise had matched the war effort so much that we ended up with not only having the full meetings, but some meetings there were 230 people attended because Philadelphia was flooded with people in microbiology research. So continue, the branch membership was at 300 by 1947 with 90 that were joint people with SOB, which is always the issue with branches. What's the percent of paid members versus national members? So the numbers started to increase pretty significantly. In 1954, we had our first woman president, Ruth Miller. Ruth Miller is a fascinating person, and it did take 34 years for the first woman president, but we have made up for it. For the last 10 presidents, 4 of them were women, and one of them, if you count the president-elect, we got 5 out of 10. So we made up for those 34 years. But to be truthful, there was almost no other female PhD microbiologist that she was extremely active in the branch. And she was a graduate of the College of Pharmacy and Science, got her master's and a PhD there, her PhD at Penn, and then was in women's medical for a very long time as chairman of the department, as well as professor of microbiology. In 1955, the meetings were moved to the Maloney building at 36th Street on Penn's campus, 36th and Spruce, and the meetings were held there for a very long time. In 1960, the SAB changed its name to recognize that it's not just bacteriology to microbiology. And in 1961, we officially changed our bylaws from the SAB chapter to the Eastern Pennsylvania branch of ASM. In 1966, there was a lot of, it wasn't a very peaceful year for the branch. There was a lot of contention that the branch was moving in different directions, and the clinical microbiologists were increasing in numbers exponentially, and they felt the monthly meetings weren't filling the needs. And they had complained, but they felt nobody was taking action. So in 1967, we had 70 branch members got together at the public health buildings on Bainbridge Street, that's still there. And the decision was, do we split or do we have a joint effort? So there was tremendous amount of negotiation. And luckily they said, we're not going to split, we'll be part of the branch, but it's going to have a clinical steering committee with many, many subcommittees. And the only joint committee with the branch was really the symposium committee. So the clinical steering committee just took off. Clinical meetings were on Monday nights and the regular branch meetings were on Tuesday nights. And not to confuse, so we had the pure number system for the branch meetings. The clinical meetings got a separate number system, so they're not included in that 780. In 1969, they had their first workshop on fluorescent antibodies, and that lasted for the workshop program lasted for 40 years. And in some years, we had four workshops a year. The first clinical symposium was on rubella in 1969, and that continues to the present time as our November clinical symposium, run in the last 10 years by Al Evangelista and his committee. So we've kept that tradition going since 1969. And the first 20 meetings also resulted in a book published by Plenum and Park Press. And those books sold. Clinical symposiums were not too common in 1969. So those books sold much more than they thought, and our royalties were significant for many, many years. In 1972, at the annual ASM meeting here, we introduced topics in clinical microbiology. And this is a fascinating story. It started with Dr. Morton and Jim Pryor saying, well, what we need is, there's so much teaching needed for the bench level in doing microbiology. We're going to put a kit together. So, and Williams and Wilkins said, oh, we're very interested in it, because they knew we were selling all these books. And they had no idea how much the topics in clinical micro were going to sell. It's a box. You bought a box for like $70. The box, in those days, that was expensive. The box contained a manual on everything you want to know about doing bench clinical microbiology. And the other unique thing is it had slides that went along with it. And so the manual, the slides, and tapes. So it sold like hotcakes, and it not only sold in the United States, it sold in Europe, and the significant royalties on that came to the branch. Also in 1972, we had our first basic science symposium on virus tumorigenesis, and the basic science symposium was in addition to the other symposium, and the differences is that was in a different months, and a lot of those resulted in books. By 1973, the attendance of the different meetings forced the merger. In August, we met, everybody had discussions. It ended up that the clinical meetings on Monday night had about 100 or 100 plus attendance, and the regular branch meetings, some of them were down to less than 10. So it showed that we had to do something. So in 1973, the decision was we're all one branch, and what the solution was, the clinical steering committee became part of the governance of the branch, and it became the executive committee. So starting the last phase of our history, phase 5, starting in 1973 to the present time, the executive committee was now running the branch, and it was a very big committee with many standing committees. There were like 15 standing committees with things like publicity and publications, and all the standard education in those too. In 1976, we had the first Stuart Mudd lecture, and that lasted 19 years. And the reason that's important is that was a special meeting each year with a special dinner, a plaque, the Mudd representatives of the Mudd family, and it became one of the leading events of the year. And it was to honor Stuart Mudd's graduate students and people that worked and associated with him. And it lasted 19 years. In 1977, we expanded to a new monthly newsletter, and that the monthly newsletters really were very significant in unifying the branch. The newsletters every month brought all the disciplines together, gave everybody a chance to participate in the branch, and was extremely popular, and that lasted many years. In '85, we had the first poster night, which again was an innovation. In '87, we had the 500th meeting. And by 1987, we had 800 branch members, 800 paid branch members. And Dr. Mandel's goal, who was the president, Dr. Mandel's goal was we're going to get 1,000 members. And it almost worked. We got, I think the highest was 951 was our big total of paid members. In 1992 was a very interesting event. They decided Penn decided we're going to tear down the laboratory of hygiene because the building is getting so old. So there was a massive movement at Penn to save the laboratory of hygiene. It was called Smith Hall by that time. And in 1992, we had a very big meeting at the laboratory of hygiene with our branch meeting with a lot of extra Penn people and everybody involved. was a very successful meeting from one aspect. It wasn't too big for the branch. Most of the branch members, when they came out of touring the building, said, "Oh my God, it's falling apart inside. If they're going to tear it down and put up a huge technology building that's going to hire a lot of microbiologists, go ahead and do it." So during the summer, they did tear the building down. And I'll show you pictures of that in a little bit. In 1992, we had our first infection and immunology forum that lasts to this time. Currently, that's run by the student chapter. But again, from 1992, unbroken meetings. In 1996, we had the Distinguished Branch Member Series. After 19 years of the Stuart Mud, we had the habit of having these big meetings once a year. So the special meeting became the Distinguished Branch Member Meeting, and that lasted for 10 years. After 19 years, they ran out of people connected with Stuart Mud. That's why we changed to this. Continuing this last phase, in 1997, the website was created, and the website really replaced the newsletter, eventually replaced the newsletter, and it replaced the meeting notices. And so that became our main our prime communication method to this day. And the current student chapter we had several other student chapters that come and go. The current student chapter was approved in 1997. In 1909 was a special year because when the ASM met here, they presented the Laboratory of Hygiene plaque, which was the ASM milestones in microbiology. And the ASM designated the Laboratory of Hygiene as the third miles in microbiology, which is a big honor. We had a big plaque ceremony, and I'll show you pictures of that in a minute. Also in 2009, we had a special meeting at the College of Physicians to give time to really discuss the history of Philadelphia micro. And it was a special branch meeting. It was also a book signing of the book on our history, and a very successful event. In 2014 is very special for me and for us that our branch was accepted at Thomas Jefferson University at the Scott Memorial Library to deposit our branch, our archives there. So if you go to our website, there's a complete index of all of the material that's in our archives. And it's a tremendous resource for anybody who's interested in our history. And it's a big feather in our caps because I don't think any other branch has an official archive with an archivist there and people to help you if you want to go through the archives. Up to 2020, we had the University of the Sciences Student Center chapter, which another new chapter, which we're very happy to have that group of students too. And in 2020, we had our first virtual executive meeting and our first virtual Monday night meeting, which again was a big milestone after 100 years. And we also had our 100th anniversary. So in closing, I'd like to show you this is the plaque that now is located at the building that was put up in place of the Laboratory of Hygiene. And it's also recognizes Dr. Berge as our founder and his contributions to ASM. And this is what it looks like now. It's at a great place on campus. It's there's a green area beside it. And if you look in this building, the very corner that's facing you, that's where the plaque is. And there's two plaques there. And you don't have to go into the building to see the plaque. So I don't know how many of you saw the plaque, but I wish more people would visit our plaque. If you're near your Penn's campus, you don't have to go into the building. It's beautiful, it's gorgeous, and it's there. And if you look at the two trees on the left and go to the second floor, if the building was still there, that would be Dr. Berge's office. And he had that from his entire time at Penn. This is the Scott Memorial Library on Walnut Street. Our archives are on that second floor there. Beautiful building, beautiful archives. Visit the website, learn what's in our archives, and you'll see more on history. So in conclusion, we're not the first branch, but we are the most active branch for the longest time. Monthly meetings for 100 years is a rather unique challenge for any branch to meet. But the big challenge is, I think, is even as our president had mentioned, we adapted in those 100 years to all the changes in microbiology and made tremendous efforts to balance academic and clinical microbiology with research and the others. And we were very successful at it. We also had 100 years of innovations, particularly for subjects covered. Education, we can't stress enough. The reason I spent time on the history of Philadelphia beforehand, it showed that Philadelphia was unique in having having 5 med schools and researchers and all this other, that education was always one of the key elements from the beginning of our branch to the present time. So we have all those innovations and symposiums, workshops, before other branches even had the ideas. And right now, our student chapter is very important to us. Not only do they run the forums, but we listen to the student chapter to guide us on where microbiology is going. And we also have had many innovations in governance that changed over the years, just to name a few of our innovations. So we look forward to adapting to the next 100 years. It kills me to jam so much of our history into one 30-minute presentation. And I know I'm going to be killed if I go over, so I tried it as best I can. If you want more information that you ever want to know on our branch, you can also get this book. I think we're the only branch that has a published book. So thank you very much, and that's it.
Okay. Thank you so much, Jim. We really appreciate that. As always, that was a great summary. And we're going to have time at the very end for questions. So I'm going to ask everyone to remember your questions and hold them till the end. We'll be using a function in Zoom that is called, it's a function where you can raise your hand, but I'll explain how that works later. We're going to keep moving so that we can, keep on time. So our next speaker is Dr. Alan Evangelista. Alan is Director of Microbiology, Virology, and Molecular Diagnostics in the Department of Pathology, and Laboratory Medicine at St. Christopher's Hospital for Children in Philadelphia. Alan is also a clinical professor in the Department of Pathology and Laboratory Medicine in the Department of Pediatrics at Drexel University College of Medicine. Prior to joining St. Christopher's Hospital, Alan was Director of Microbiology at Johnson & Johnson. And I think that gives Alan a really great perspective to kind of understand antimicrobial resistance, both from the side of a clinical microbiologist in a hospital and also in pharmaceutical drug development. Alan has published numerous abstracts, papers, and book chapters. He was our branch president in 1991. And as Jim said, he co-chaired our symposium for 10 years, which is quite a feat. Alan is going to talk about the historic and current threats of increasing antimicrobial resistance. Alan.
Thank you, Linda, and thank you, Jim, for both of you putting this together, and for Toby Eisenstein for your input. It's a real pleasure to be part of this, and it was really a lot of fun putting some information together with the help of Jim's book, and I do recommend the book because it does help put some things in perspective. What I'd like to do today or this evening is to review, start off with the CDC. It's always a good place to start because, what are the threats? And they have interesting levels of serious threats and really urgent threats. And we'll look at that. We'll just quickly review the mechanisms of resistance and look at a clinical case. The cases now that are most interest to a lot of the hospitals are carbapenem resistance. It is a reportable infection to the Philadelphia Department of Health. So we'll look at that. We'll look at some of the history to follow up what Jim was talking about, some of the early information on microbial resistance, especially in vitro susceptibility testing, came from the Eastern Pennsylvania branch of the ASM. A quick look at some of the beta-lactamases, how they've evolved and what's happening currently in the US and in Philadelphia, and also look at some treatment options. So we'll start off with the CDC slide. It's always nice to start with an area like this for the most recent. It's dated 2013, but it really was up. Was presented in 2016, and it really hasn't changed over the time. The focus of urgent is the carbapenem-resistant Enterobacteriaceae, which are currently a threat. Serious levels, VRE, MRSA, I'm going to focus on that, as well as the ESBL, the extended spectrum beta-lactamases. So this is an interesting slide. I got this from the website called The Economist. It's actually a newsletter. And it talks about the new antibiotic approvals. And it shows us that where we are in the last decade, from 2010 to the present time, is about where we were in the 1940s. There aren't a lot of new antibiotic approvals occurring. There was a real shortage of antibiotics in the early 2000s, as you can see, probably the lowest level here. And the opposite of that was a lot of antibiotics being approved in the 1980s, when we had a lot of the cephalosporins and the introduction of the carbapenems. The good news is that in 2019, the CDC said, well, in the last few years, we have seen decreases in some of these threats. We're seeing nationwide about a 40% decrease in Enterococcus. This is highly dependent upon the hospital and infection control procedures that are in place. As far as the methicillin-resistant Staph aureus, it's about a 20% drop. We've seen that at our hospital also, about a 20% drop in the last 10 years. Unfortunately, carbapenem resistance is not dropping. It's stable, so it's still a threat, and it's still out there. So major mechanisms, how do we describe these? This is how I tend to look at the mechanisms in three buckets. There's reduced drug accumulation, meaning efflux pumps or a decrease in porin channels. There are inactivating enzymes. Most of the enzymes are focused against beta-lactamases and aminoglycosides. There are alteration of drug targets, the major target being a penicillin binding protein target. We see that it could be an altered target that occurs over time, as we see with Strep pneumoniae. There's also targets in ribosomal binding sites. And then there's examples listed here. There's also some mutations and alterations in lipopolysaccharides, which is concerning because polymyxin B resistance now in Acinetobacter is increasing. So what's an example of a current threat? I guess the easiest way to look at this would be to take a case study and present this. So I'll present this is a 6-week-old male who had a urinary tract infection. He was transferred from another hospital. He was admitted to our neonatal intensive care unit with a fever. Blood cultures were done. They were negative. Catheterized urine culture was positive. On hospital day 2, it grew greater than 10 to the 5th, a gram-negative rod, which was a lactose fermenter. And here's the end result of that culture. It was Kleb pneumoniae, which was an NDM by PCR. Here's your classic pattern of resistance that we're seeing with using a Vitek. The additional antimicrobials using E-test and some of the newer agents here, but it was only susceptible to amikacin right at the break point. Fortunately, it was a UTI, so we knew that you'd get a lot higher levels in the urine. It was susceptible to fosfomycin as a last case resort, and Meropenem abrobactam at the break point also. The patient was treated with amikacin, fever effervesced, and there was more clinical improvement. So fortunately, even though it was one of the worst, because this is a metallo-beta-lactamase, now we do have a newer agent for metallo-beta-lactamases, but at the time it was either Meropenem abrobactam, which really doesn't have an indication for that, but or fortunately the aminoglycoside. So now, when did antimicrobial resistance, when was it first reported? Well, let's go back and look at the history of antimicrobial agents first. So we go all the way back to 1910. Paul Ehrlich was successful in isolating arsphenamine and neo-arsphenamine. He was working with a chemical company in Germany, which later became Herbst Pharmaceutical, but they were looking for agents that they could use it for syphilis. And he found that these particular agents were very active against Treponema pallidum and also African trypanosomiasis, which was a big concern at the time as well. Syphilis, the patients suffering from tertiary syphilis were undergoing a lot of CNS side effects, including paralysis. And this was one therapy that seemed to work. This is a derivative of arsenic. It's an organic form of arsenic. So the organic forms are not as toxic as the inorganic forms. And he termed the phrase chemotherapy. He was the first one to use that. Just in perspective, 10 years later was the first meeting of the Eastern Pennsylvania chapter. So we'll put that in perspective. And then, of course, Alexander Fleming and penicillin back in 1928. Reading his history is interesting too, because it's described as a series of chance of events. And he found that a mold, penicillium, was growing, and it was inhibiting staphylococci and some other gram-positives and also H. influenza. It was staphylococcus growing on a plate that had been inadvertently tossed away. And then when he looked at it, he was finding inhibition from molds. And he went on to look at a lot of other details as well, as far as broth, growth of molds. And when he had broth cultures, it was either growing a mold or bacterium, but not both. So a certain indication is that molds were capable of inhibiting bacteria. He did publish a paper in 1929, but he couldn't purify penicillin. It was a fairly unstable compound, so he had difficulty purifying it. So that sort of stayed hidden for the next 10 years. In the meantime, another investigator, Gerhard Domack in Germany, was working with sulfanilamide, and this was very active in animals in preventing infections, but couldn't come up with an in vitro test. And then in 1939, Ernst Kayan and Howard Florey in the UK were able to purify penicillin with the help of Heatley, who was a mycologist. And they were not only purifying it, but actually ended up using it in animals and in patients and used it as a chemotherapeutic agent. They published their findings in Lancet in 1940. So it wasn't, and then that same year, so this is in a situation where you have a discovery of a new drug that actually can fight Staph aureus infections and a number of other infections, but they were also able to find an enzyme that was able to destroy penicillin. It turns out to be that enzyme that they published was from E. coli, and years later it was recognized as an AMP-C beta-lactamase. So this was determined even before it was widely used. Now, a penicillinase from staph was identified in 1944 by Kirby, and this is a highly potent penicillin inactivator. This was published in Science in 1944. And then through the 40s and early 50s, pen-resistant Staph aureus emerged. Vancomycin was discovered by Eli Lilly in 48, but not introduced until 10 years later. Methicillin was introduced in 59. 2 years later, MRSA is identified by Patricia Jevons. She worked at the Staph Reference Laboratory, had a lot of reference isolates of Staphylococci, and was able to find a Celbenin-resistant staph. Celbenin was the trade name for methicillin at the time. So here's a quick overview of years of release of a particular agent and when resistance was first identified. You see, there's not much of a lag time for most of these agents. For sulfonamide, 1937 to 38, we start to see Staph aureus resistant to the sulfa drugs. For penicillin, it was the same year, and then for Staph aureus, a year later, and then eventually for strep pneumoniae, when you're getting an altered target, this is the penicillinase enzyme, and then you have altered target here. Streptomycin, Selman Waxman was the first to coin the term antibiotic. So this was grown by Streptomyces griseus. He isolated streptomycin, and this became valuable for the treatment of tuberculosis. But of course, during therapy, strep-resistant strains were identified. Vancomycin came out in 1958, and VRE was first described in 1960. So only 2 years later, we have plasmid-mediated VRE, which is a transposon, which has the VAN-A gene on it. Methicillin 1959, 2 years later, MRSA, and then cephalosporins were first discovered in 1945. It was several years later where semi-synthetic derivations of the cephalosporins had been developed. And cephalothin, the same year we found cephalothin resist. We didn't. I mean, it was reported of broad-spectrum beta-lactamases. Ampho-B coming out in 59 and was a long time before Candida became resistant. And unfortunately, now we have Candida auris, which is a fluconazole and sometimes voriconazole resistant. And now we're seeing some strains that are amphotericin B resistant. Cefotaxime was the first third-generation cephalosporin released in 1980. And then we're seeing resistance here. Azithromycin, imipenem is a big one. 1985, it comes out. 96, the KPC producing Klebpneumo were first described. Daptomycin, a year later, we see resistance. Ceftaroline, a year later, we see resistance. And ceftaz-avibactam, the same year, we see resistance that are KPC Klebpneumo. Here's a historic note from our branch. This was 1947. So Amedeo Bondi, Meade Bondi, Earl Spaulding, Dorothy Smith, and Catherine Dietz, all from Temple University Medical School, published a method using a disc test. There were several investigators during the 40s using wells and filter paper strips and depressions in agar and all types of methods trying to describe susceptibility testing. But Meade Bondi was the first to take the disc that we currently use. It's a 6 millimeter, 6.5 millimeter disc. They published the paper in the American Journal of Medical Sciences in 1947. They happened to be using blood agar as their agar of choice here. And there weren't too many drugs at the time. They were testing penicillin and sulfa drugs. Later that year, Meade Bondi transferred over to Hahnemann University. He became chair of the Department of Microbiology and published a number of articles on both the penicillinase producing bacteria, also investigated methicillin, oxacillin types of penicillins. And this is a review article about antibiotic resistant Staph aureus with all of these antimicrobials listed. 10 years later, Bauer, Kirby, Sherris, and Turk then published a standardized method using the Bondi disc, but then using Mueller-Hinton agar and standardized method. This later became adopted by the Clinical and Laboratory Standards Institute. So looking back at some of the symposia, Jim mentioned some of the symposia, and there's a little smattering of symposia, maybe one each decade, talking about antibiotics and antimicrobial resistance. In 1942, it wasn't a symposium, it was a presentation at a branch meeting, but Selman Waxman at the time was president of the Society of American Bacteriologists, and he presented a talk on the production of antibiotic agents by microorganisms and its significance in natural processes, an interesting concept for the time. So here we have the seventh symposium in a series by the Eastern Pennsylvania branch. And interestingly, it was co-chaired by Meade Bondi and Jay Satz. Meade was Bondi from Hahnemann and Jay Satz from Temple. In '85, there was another symposium on antimicrobials. Here we have Jim Poupard, Bruce Klager, Laurie Walsh in '91, Don Yunkin and Henry Fremow and others, Irv Nishamkin and Jim Poupard in 2004, co-chairing. Linda Miller, Anna Feldman-Rosen in 2008, and myself, Kelvin Albee, and Kaidi Ota Sullivan in 2017. So where are we now? What are about the trends that we're looking at over the past 40 years? It's not good news from the 80s and 90s and the early 2000s. Here we see MRSA rates going up. These are data from the CDC that was published by the ID Society in an article called Bad Bugs, No Drugs back in 2004. We see VRE increasing in the 90s and the early 2000s, and we see fluoroquinolone resistant Pseudomonas also increasing at that time. The good news is that with the use of infection prevention and more attention to antimicrobial stewardship, MRSA rates went down over this period into the present time. So this is where we're seeing the decrease in MRSA, a slight decrease also in MSSA. VRE Same story. During the 80s and 90s, we see an increase. These gold bars here, the yellow bars, are usage of vancomycin. And then the red line here are the VRE rates, also paralleling that. Into the late 90s and the early 2000s, we're seeing VRE as a problem. Again, in the last couple of years, we're starting to finally see VRE decrease. And it depends locally where you are. 41% is listed here in this data from the CDC. In some areas, it's maybe a 20 or 30% decrease. Now, what about carbapenem-resistant CRE? Well, we know that there's several classifications for beta-lactamases. A class A are the extended spectrum beta-lactamases and the carbapenemases that have serine at the active site, like KPC, the Kleb-Pneumo-producing carbapenemase. Class B are the metallo-beta-lactamases. These are a little more serious because there's not a lot of antimicrobial agents that are active against the NDM, VIM, and IMP type of carbapenemases. Class C are the cephalosporinases, very high levels of resistance against cephalosporins, including the third generation cephalosporins. And most of these are the CMY, ACT, and FOX type of AMP-C types. And then class D are the carbapenemases like the OXA48. So this is an example of a Kleb-pneumoniae with different elements. Typically, if you see a community-acquired Kleb-pneumo, you're going to have ampicillin resistance. If you're looking at an ESBL, they're resistant to the third generations. AMP-C is also resistant to cefoxitin. So here's a phenotypic marker. And even though cefepime is susceptible in vitro, it doesn't usually work, and neither does piptazo in patients in clinical data that was published in the IDSA and CID in 2014. Cefepime does work against AMP-C, and then CRE have all the pan resistance. So where are we with KPCs? Well, in the last few years, all 50 states now, as of 2017, the last data that was available from the CDC. So we're going from 44 states to 50 states in about a 5-year period. For the NDMs, it's even more concerning because it was 11 states back in 2013. Now it's up to 34 states in 2017. It has leveled off, and it's probably a little higher than that now. OXA48 went from 5 states to 28 to 27 states. What's happening locally? In Philadelphia, since it's a reportable infection, and this is the most recent data that I was able to obtain because it's pre-COVID. With COVID, a lot of surveillance is focused now on COVID. But we're still seeing, we're seeing KPC, we're seeing NDM, and we are seeing OXA48 locally. Where are they occurring? Mostly in urine, respiratory, and wound infections. It's about 82% of the CREs. And what about newer agents? We had ceftolozane tazobactam approved in December of 2014. Good activity against multi-drug resistant Pseudomonas, but not so much against KPC or the metallos. Ceft has avibactam, a little bit better. This does cover KPC, but not the metallo-beta-lactamases. Then along comes meropenem-vaborbactam in August of 2017. Vaborbactam is a different type of beta-lactamase inhibitor. It's a cyclic boronate, so it does have activity against KPC. Unfortunately, not active against NBL. And now we have cefiderocol. November of last year, that got approved. It's a siderophore in addition to a cephalosporin, so it uses ion channel uptake, and it does hit the metallo-beta-lactamases. A little challenging for e-test, but available as a disc for doing disc susceptibility testing. So in summary, where are we? The MRSA and VRE resistance definitely increased from the period of 1980 to 2010, and now we're seeing a little bit of a decrease here. It's still out there. It's still a concern, especially with VRE. Resistance historically has been detected shortly after the introduction, so there's not too much of a time lag. It's always going to be with us. We do know that a lot of our members were involved in the early agar disc diffusion method and a number of publications in the 40s and 50s. Carbapenem resistance has increased but remains stable. Still out there, still a concern. And we know that there aren't a lot of options. There are, fortunately, a few options for carbapenem resistant organisms, but it's been very slow progress. So thank you very much for this opportunity to be a part of this great meeting. It's a pleasure being part part of the branch and being part of this. And thank you very much, Linda, for this opportunity.
Thank you, Alan. Thanks so much for a great talk, a great summary of the challenging issues we have in antimicrobial resistance. So to keep us moving, I'm next going to introduce our next speaker, which is Dr. Irv Nishamkin. Irv is currently a professor of pathology and laboratory medicine in the Perelman School of Medicine at the University of Pennsylvania. Irv served as the 10th director of the William Pepper Laboratory of Clinical Medicine, which I thought this was cool, was established in 1895, and it was the first clinical laboratory associated with an academic center. Irv is also the associate director of clinical microbiology of the Clinical Microbiology Laboratory at the Hospital of the University of Pennsylvania from 1982 until present time. Irv has authored or co-authored lots and lots of publications, over 225 peer-reviewed research publications. And importantly for us, and fortunately for us in the branch, he's been really active in our branch since the early 80s. He was also one of our branch presidents. That was from 1999 to 2001. Irv has also been very active with ASM National, serving on numerous committees, and has also been an editor-in-chief of Clinical Microbiology Reviews. So it is with great pleasure that I introduce Dr. Irv Nishamkin, who's going to talk about a century of diagnostic microbiology advances with contributions by the Eastern Pennsylvania branch ASM. Thanks, Irv.
Okay, thanks, Linda. So far, this has been just such an interesting afternoon of history, and we're going to focus now on a little bit on advances in diagnostic microbiology. And there has just been so many advances in clinical microbiology over the last 100 years. It's impossible to cover this in 20 minutes. So I'm really going to just focus on a few topics, things that I found interesting. Some of you may be aware of many of these advances, and some little pearls as well. And I'm going to just throw in a little bit of national timeline with this, and we'll get started. So the 1920s to 40s was a very active time in clinical microbiology, and this is, you're going to see this throughout the talk. It's just a timeline of advances at the national level, and I've taken some of these pieces from ASM website and some other sources, but we're all familiar with some of these major advances in clinical that relate to clinical microbiology. We have to talk about blood cultures. One is it's an area of major importance in terms of infectious diseases, and of real interest was blood cultures was a big topic in the early 1920s in the 20th century, and this is a photograph of the first commercial blood culture system. It was produced by a company called Hinson, Westcott and Dunning, and some of you may have, some of the old timers may remember that, but that company was bought by Becton Dickinson. And it's no wonder, Becton Dickinson has a big interest in blood culture technology. But the first commercial system here was published by Judd and Simon. The actual blood culture device was produced in Philadelphia by the Steel Glass Company of Philadelphia, and it contained 15 to 25 cc's of glucose, they call it glucose bouillon, so it had meat broth. It was citrated as an anticoagulant, and you put 5 cc's of blood into this. And I think the thing of interest was the comment in the paper that said a single negative result is rarely of value. That's still true today. And frequent examinations wouldn't be tolerated by the patient, to whom a vein puncture with a large needle is by no means an indifferent procedure. So over 100 years ago, they were complaining about needle sticks. And the branch devoted quite a few workshops and symposia on blood cultures. Our branch members from all the institutions across Philadelphia, the 5 medical schools, the other independent hospitals, all published in one form or another papers on blood culture technology, evaluations of different blood culture media, techniques, etc. And this is just an example of some of the workshops and symposia that the branch has sponsored over the years. Most recently in November, a year ago before the lockdown, we had a symposium called Innovative Approaches to the Detection of Bloodstream Infections. And it was co-chaired by Alan Evangelista, Matt Pettengill, and Laurel Glazer. So by the mid-70s, most labs were using some form of automated blood culture system, from the Bactex to the DIFCO system, Bacti alert system, and they had different types of detection system. The radiometric system, which was really kind of the first automated system, went by the wayside to infrared and fluorescent technology. And then, of course, this is some of the systems that are being used today. These are all continuous monitoring systems, and they all have fairly equivalent performance characteristics in terms of time to detection and the spectrum of organisms that are detected in different bottles. So a lot of technology, and these systems are getting smaller. You can do more blood cultures in less space with these systems. And then in the 40s, there was a lot of emphasis around STI diagnosis, and particularly syphilis. And you can see here in the left-hand corner of the slide, the number of cases of syphilis in the United States was approaching 500,000-600,000 cases a year in the 40s and 50s. And with early syphilis in the hundreds of thousands. In Philadelphia, microbiologists and physicians played a really important role in syphilis diagnosis. Two well-known microbiologists, Fred Borner and John Colmer. Fred from Graduate Hospital at the time was part of the University of Pennsylvania. And John Colmer at Temple University. And we devoted a lot of meetings in the 30s and 40s to syphilis. There were 5 in about 10 years time. And one of the highlights here, which I point out, was a preliminary report on the Washington Serology Conference. And this is where 19 what they called serologists, these were scientists and microbiologists that were involved in developing syphilis diagnostics, all met to talk about their dozens of different technologies. And 2 featured scientists, Fred Borner and John Colmer, were part of that conference. And you can see here Fred Borner with their flocculation test for syphilis, and Colmer with their complement fixation test. And these are the 2 key papers that were published by Colmer and Borner. And you can see here an example of the macro flocculation test that was developed. Very similar to the VDRL test that's still used. And then these special slides called the Borner slide for doing these microflocculation tests. And you can still find these slides on Wheaton website, Fisher Scientific, and others. They still sell these. So they're still around, and they've had a really lasting effect on syphilis diagnosis. And then the 50s and 60s, again, very active in microbiology. As Jim mentioned, we became the ASM in 1960, Watson and Crick, and our local Philadelphia branch members, Bruce Blumberg and Irving Millman, were major individuals in the discovery of HPV and vaccine development. And then in the 60s, again, advances in susceptibility testing and microbial classification. In the late 60s, Werner and Gertrude Henley at Children's Hospital were doing a lot of research on EBV, and they had established the association of EBV with Burkitt's lymphoma. And this is a key paper that came out of their lab, essentially identifying EBV as the cause of infectious mononucleosis. And of course, EBV is also known to be the associated cause of other malignancies. So this was a major finding out of Philadelphia in the 60s. And then a lot of activity in clinical microbiology on microbial classification and identification. And in the early days, some of the, again, the older timers in the group will remember we used phenotypic expression of various enzymes and other chemical reactions to characterize bacteria. This was a study on isolates of the members of the Mime tribe, now known as Acinetobacter, by Eileen Randall and Elizabeth Leniger from Thomas Jefferson University. And you can see, again, this is one of the tables that they published in their paper, showing the different phenotypic profiles of then the different genus within this tribe. And and we used two biochemicals in those days to perform these biochemical reactions. Shown here is like triple sugar iron agar and the indole reaction and the OF glucose reaction. And you'll notice the caps on these tubes to allow circulation of air. Well, this was an invention of branch member Harry Morton, who was the director of clinical microbiology in the Pepper lab at Penn. And here's a copy of from his patent in 1939. And here's a picture of the current version of these metal test tube enclosures, which again are still available commercially. And they're called the Morton steel enclosures and developed here in Philadelphia. Of course, susceptibility testing has been really important in clinical microbiology. And one of the major devices that was developed in Philadelphia was something called the Steers replicator by Ed Steers, who was the director of microbiology at the Pepper lab at the Hospital University of Pennsylvania in 1960. And this is developed by Steers, Foltz, and Betty Graves, all in our Pepper laboratory. Again, this is a device that is used widely worldwide and is still available today for replica plating. And again, an example using agar dilution. And then we went from two biochemicals to really more miniaturization in the 70s. And some of you'll remember the API system, which was patented in the mid 70s, where they took essentially the two biochemical reactions and put them into a little strip. And we had incubators full of these miniaturized strips, and they were really, it was a major advance at the time for microbiology. Today, things have become even smaller and more automated, and this is just examples of some of the commercial systems that miniaturized identification and susceptibility testing. Not the only companies, but three of the major ones that are out there. And then by the late 90s, we were getting into more molecular diagnostics and molecular technology. And sequencing of certain housekeeping genes started to come to the forefront for microbial identification. We started to use 16S sequencing in our laboratory in the late 90s. Matter of fact, we were one of the early converters of all molecular identification in our mycobacteriology lab in the late 90s and early 2000s, and got rid of biochemical testing. Today, and what emerged in the 2000s were the use of MALDI-TOF and the for rapid identification of bacteria, mycobacteria and fungi. There are two major systems that are in wide use worldwide now. And they've been a real game changer in terms of how we do things in the microbiology lab, not just from the speed and accuracy, but also from the cost. And it really had a major positive impact cost-wise on the laboratory. And branch members, spent a lot of time evaluating MALDI technology, and not just their technical specifications and performance, but also the clinical utility and impact on this, again, from all the major institutions in the city. Next generation sequencing emerged in the late 2000s. And has still been restricted to really novel infection discovery, microbial typing, investigations in outbreaks, of course, whole genome sequencing for a variety, for more microbial pathogenesis, but still not ready yet for routine use in diagnostics. And we're just trying now to identify use cases for using next-gen sequencing technology for really difficult to diagnose infections. But this is just, I put this paper, a recent paper from Children's Hospital on identifying enterovirus D68 with acute flaccid myelitis. And this was in an EID paper last year. I want to mention something about anaerobes and the microbiome. Jim, in his discussion of the history, talked about the war years and anaerobic infections, while Harry Morton was very interested in anaerobic infections, as well as other microbiologists in Philadelphia, like Earl Spalding, for example, and Len Zabricki, I'll mention in a second. But Harry published this paper in the Journal of Bacteriology, which I had to laugh about. But basically, in this first paragraph of this paper, he says, after experiencing 3 explosions in the course of 1 year in our laboratory, they decided to investigate the particular technique for generating anaerobic conditions in the laboratory. And he goes on to describe a method that generated less hydrogen in the anaerobic jars, and was much safer to grow anaerobes. One of the interesting things which I found during researching this talk was that Len Zabricki and Earl Spalding and Temple really did a lot of early, what we would now call microbiome studies. And this paper from J. Beck in '62 was on what they call the stability of the normal human fecal flora. And by any other words, this is microbiome. And this table shows the actual concentration of aerobic and anaerobic bacteria in different subjects. And they were looking how they varied from one person to the next. So this is clearly early microbiome research coming out of Philadelphia. And then have to mention Russ Shadler. Russ Shadler was the chair of the Department of Microbiology at Jefferson Medical College. And Russ was a big supporter for Eastern Pennsylvania branch. We helped host the meetings at Thomas Jefferson University while he was chair. And he did a lot of work on microecology of the intestinal tract in animal models. He worked with the famous Rene Dubos at Rockefeller Institute. And still today, you can purchase what's called Shadler broth, and this is based on a 65 paper for growing anaerobic bacteria, and it's used, clinically in laboratories. So it's kind of had a lasting effect with his name on it. And then the 70s, we get the 70s and 80s, and of course, again, many discoveries during that time. We had an ASM meeting in Philadelphia in 72. The end of the 80s was, brought on the discovery of PCR by Carrie Mullis. And then during that time, there was a real interest in STI research in Philadelphia, and particularly gonorrhea. And diagnosis of gonorrhea was really primarily culture-based in gram stain in the early days, now done by molecular diagnosis. Again, many of our branch members have published on various aspects from culture to culture-independent detection of STIs, particularly Neisseria, gonorrhea, and chlamydia, going back to Harry Morton's days in the 40s. And one of the early developers of a kind of a culture and molecular-based diagnostic was Len Zabricki at Temple, and using a transformation test. And he had this temperature-sensitive mutant of Neisseria gonorrhea, which he used for diagnosis. So that's, again, early discovery. And then medical mycology was very big in Philadelphia. Temple University is really a center of excellence in medical mycology. And these are some names that some of you may remember: Billy Cooper early on, Helen Buckley, who's a leading figure in mycology, and Fritz Blank, all at Temple University. And I just point out a couple of key papers that came out of Fritz Blank's lab on using certain specific differential media for Cryptococcus neoformans, which we now know is birdseed agar. So these came out of Philadelphia laboratories. And then I'm going to finish up here. Turn this off. I'm sorry. And the 90s and 2000s, again, major advances. Richard Crowell, who was at Hahnemann University, was elected president of the ASM. And we had a general meeting of the ASM in Philadelphia about 10 years ago. And lastly, I just want to mention that besides Fritz Blank at Temple University, we had another Fritz Blank. This is the Fritz Blank, who's the owner and chef of a very famous French restaurant called Du Cheminée on Locust Street. He was a microbiologist and a world-renowned French chef. He was a big supporter for the Eastern Pennsylvania branch. He hosted many of our branch symposium and workshop dinners over the years before he retired and sold his business, and he passed away a number of years ago. So that's a kind of a brief history of some diagnostic microbiology with some contributions from our branch members.
Thank you so much. That was great. A really nice overview of such an important area. I'm going to turn it over now to Dr. Toby Eisenstein, who's going to introduce the next two speakers. And before I do, I'm just going to take 5 seconds to thank Toby. She really came up. She really did a lot of hard thinking about this symposium and came up with ideas for topics and linking the present to the past. And she just did a great job. So I'm excited for Toby now to introduce the next two talks. So over to you, Toby.
Okay, well, the next two talks are oriented towards basic science. And as Jim gave you that beautiful overview, our branch had a very strong clinical group of people, but we also had a very strong group of basic scientists in Philadelphia with all the medical schools and all the research going on. And luckily, our branch did not split. And over the years, we've been able to keep the two things together. And I think they've been very synergistic. For myself, having the contact with the clinical microbiologist has been fantastic because as I teach the medical students, but I'm not in a clinical lab, I always learn something new that I can use in my teaching. Well, we're going to turn now to two lectures that are on basic science. And the first one is going to be given by Dr. Sunny Shin. Dr. Shin is an associate professor in the Department of Microbiology at the University of Pennsylvania Perelman School of Medicine. She has a very distinguished background. She received her BS in biology from MIT, her PhD in microbiology and immunology from Stanford University School of Medicine, and did her postdoctoral training in the Department of Microbial Pathogenesis at Yale University School of Medicine. So you can't get much better than that in terms of your credentials. Her current research program encompasses the fields of bacterial pathogenesis and innate immunity, with a focus on the bacterial pathogens Legionella pneumophila, Coxiella burnetii, and Salmonella typhimurium. And she's doing some really cutting edge work on how these organisms trigger innate immunity and how that interacts with the adaptive immune response. Her laboratory is very well supported by the National Institutes of Health, and she's also the recipient of a Burroughs Wellcomes Fund Investigators in the Pathogenesis of Infectious Diseases Award. She's going to talk to us today about eavesdropping on bacterial host conversations, lessons learned from Legionnaire's disease. And it's a real delight to introduce Sunny Shin.
Okay, so thank you all for having me today. Thank you so much, Toby, for the kind introduction. It's really an honor to be speaking at the 100th anniversary celebration. I've been a faculty member here at Penn for about 10 years. And I have to say that the branch has been a really special part of my time here at Penn. It's been wonderful getting to know all of the basic and clinical microbiology faculty and trainees and scientists all across the Philadelphia area. And my lab has been very involved in the branch, with several of my lab members having had leadership positions within the student branch. So thank you again. And so the organizers asked me actually to give you a historical perspective on Legionnaire's disease, given the special link that the discovery of Legionnaire's disease has to Philadelphia itself. And then I'll close at the end with a little bit of the insight we've gained into understanding how Legionella causes disease and the immune response to Legionella infection. And so I want to take you back in time to 1976. Which was actually the year I was born, and also America's bicentennial. So it was the 200th anniversary of the Declaration of Independence. And here, just for fun, I'm listing who were the board members of the ASM branch at that time, including Toby, who just introduced me. She was the secretary, and I'm sure many of you are familiar with many of the names I list here on the slide. And so what also happened in 1976 was the 50th annual convention of the American Legion, which consists of former war veterans from the world wars. And so because this was a special year, they had a large number of delegates, over 4,000, travel from the Pennsylvania chapter of the American Legion to Philadelphia and stayed at the Bellevue Stratford Hotel, which for those of you who are in Philadelphia know that's right in downtown. You can't miss it. It's a huge hotel right on the corner of Broad and Walnut Streets. And they stayed at this hotel for 4 days celebrating the bicentennial and their annual meeting. And so unfortunately, shortly after this convention, there was an outbreak of an unusual type of pneumonia. Many of the attendees had muscle aches, headaches, severe coughs, diarrhea, muscle and chest pain, as well as fevers as high as 107 degrees Fahrenheit. The first person died on July 27th, just 3 days after the end of the convention. And in August, it became clear that there was a huge toll with 221 ill and 34 who succumbed to disease. Many of the victims were older in age and were smokers. However, several of the victims were quite young as 39 years of age. And so at that time, the cause of Legionnaires' disease was unknown. And I'm showing you here some headlines as well as a cover of Time magazine from that time. And so the CEZ launched its largest investigation in its history. And it deployed over 20 CEC epidemiologists, in addition to the many public health officials, workers, and laboratories who worked relentlessly to identify the cause of this disease. Jim Poupard in his book noted that in addition to the regular branch meetings that were held here in Philadelphia, there are of course many informal discussions and possible etiology and epidemiology of this new disease state. And so 6 months later, we still didn't know what the cause of Legionnaire's disease was until these two scientists became involved. So what I'm showing you here is a photo of Charles Shepard, who is the head of the leprosy and rickettsia branch of the CEC, and Joseph McDade, who is a CEC basic microbiologist. And so in December 1976, McDade finally discovered the etiology of Legionnaire's disease. So he was called into the investigation and was asked to actually rule out Q fever, which is caused by an organism related to Legionella called Coxiella burnetii that our lab also studies on as a possible agent. And so what they had observed was that in summer of 1976, that guinea pigs inoculated with lung suspensions from patients became ill and died of febrile illness. And the causative agent was actually antibiotic sensitive when passes through eggs, so suggesting that it was something of bacterial origin. And after an awkward Christmas party, actually, when Joseph McDade was actually accosted by a guest who complained to him about, he didn't understand why the CEC hadn't figured out the cause of Legionnaire's disease, Joseph McDade decided to cancel his vacation plans, and he spent countless hours during that week in between Christmas and New Year's looking over his slides and data. And that point was when he had a eureka moment and actually found that these guinea pig lung sections actually showed bacilli present within white blood cells. And furthermore, their data suggested that eggs inoculated without antibiotics and given to guinea pigs became infected, and that serum from survivors actually reacted with yolk sac isolates. And so what we know now is that Legionella bacteria consists of many different species. The one that caused Legionnaire's disease is Legionella haemophila, but Legionella are found ubiquitously throughout freshwater environments, including rivers, lakes, and streams, where the bacteria normally are found associated with biofilms, where they can infect and replicate within protozoa amoeba. And the bacteria can replicate within over a dozen different species of protozoa that have been identified. We know now that man-made technologies such as cooling towers, air conditioning units, hot tubs, and showers can allow for the aerosolization of contaminated water supplies, such as what happened in Bellevue Stratford Hotel. It was actually the cooling tower that was heavily contaminated with Legionella bacteria. And so this allows for inhalation of these water droplets containing Legionella into the human lung, where the bacteria can go on to infect alveolar macrophages and replicate to huge numbers and lead to this severe pneumonia known as Legionnaire's disease. And so we know now that those are elderly, immunocompromised individuals, for example, those on TNF blockers, as well as smokers are increased risk. And the disease has a fairly high mortality rate with about 10 to 25%. And so since then, we know now that Legionnaire's disease is like an important and ongoing public health threat. It's considered to be one of the major causes of community-acquired pneumonia. And you can see here from this graph from the CEC that Legionnaire's disease is actually on the rise in the US, where you can see that it has an exponential increase in number of cases from 2000 to 2018. In 2018, there were 10,000 cases reported within the US, and Again, in 2019, there were also another 10,000 cases, although it's thought that the number of cases are vastly underreported. And the National Academy of Sciences, Engineering, and Medicine estimates that there are probably around 70,000 cases per year in the US alone. And Paul Edelstein, who's an emeritus professor here at Penn and is a world's expert in Legionnaire's disease, estimates that there are probably at least 100,000 cases per year in the US alone. And so I'm just giving you some headlines from the news this past year. There is quite a prominent outbreak of Legionnaire's disease this past January and fall, actually, at the North Carolina Mountain State Fair that was caused by hot tubs on display. That outbreak unfortunately resulted in 4 people dying and hospitalized 96 others. And then due to the pandemic, we have this issue now of buildings that have been closed down with stagnant water collecting. And this is perfect breeding grounds for Legionella. And so there actually was a shutdown of several CEC buildings very recently because it was detected that Legionella had grown to high numbers within the CEC building water supply. And then school districts across the country have found that there is increased Legionella present within their water systems and have been having to deal with how to flush Legionella out of their water systems. In addition to, Legionella being an important public health concern, Legionella has also emerged as an excellent experimental model system for a study of actual pathogenesis, cell biology, and immunology research for many reasons. One is that it's genetically tractable. The second is that it has a really fascinating intracellular life cycle in both protozoa as well as mammalian host cells. So Legionella has become a really excellent model for understanding bacterial pathogenesis and for understanding the cell biology of membrane trafficking and other eukaryotic processes. Thirdly, because Legionella has not co-evolved with the mammalian immune system, it has not evolved to evade mammalian immune responses. And that, coupled with the fact that there are good animal models available, makes Legionella a really excellent model for understanding mammalian immune responses to infection. And so here in Philadelphia, we've had a number of scientists who've studied both clinical aspects of Legionnaire's disease as well as more basic research as well as a host response. So I'm just highlighting here a few papers from Toby Eisenstein, Paul Edelstein, Ramona Nonoibel, who's down at University of Delaware, Luke Tellney. He was an emeritus professor here at Penn and did some fundamental electron microscopy studies, really documenting how Legionella replicates within cells and transforms its phagosome. And then Irv, as well as Herman Friedman, a former member of this branch, who did some really important and seminal research in the immune response to Legionella infection. And so what we know now from the work of many researchers in the field is that in order to cause disease, Legionella is uptaken by macrophages within the lung. And once it's within the macrophage, it's able to rapidly evade destruction by the endolysosomal compartment, which is a place where bacteria would normally get killed. Instead, Legionella deploys a type 1 secretion system apparatus, which is a molecular syringe-like device that allows Legionella to inject over 300 bacterial effector proteins directly into the cytosol of the host macrophage. So these effectors have really interesting and novel cell biological activities, and this is a really active site of investigation in the field. Several of these effectors are known to manipulate the functions of RF and RAB GTPases, which are important in regulating membrane trafficking within cells. And this allows the Legionella-containing vacuole to intercept ER-derived membrane to allow it to remodel its compartment into a compartment that resembles the rough endoplasmic reticulum and is studded with ribosomes. And so it's within this compartment that the bacteria are able to replicate to huge numbers and then break out of its initial infected cell and then go on to infect neighboring cells. And so I really like to show this microscopy image. So this is actually an image that was taken by my former postdoc advisor, Craig Roy, who's a professor at Yale. And so what I'm showing you here is a macrophage, same with DAPI, where you can see the nucleus here, the macrophage. And this macrophage was infected with a single Legionella bacterium, which would be one of these rods here. And you can see that over the course of 16 hours, the bacteria replicate to huge numbers within this macrophage. And so we, as well as other groups, are really fascinated by the ability of Legionella to do this. How is Legionella able to evade innate immune defenses of the macrophage to be able to survive within this hostile environment? And in turn, how does the immune response deal with this threat and detect Legionella and mount a successful immune response that controls infection? And so we know now that from the work of many groups, including our own, that even though this type 4 secretion system is really important for the ability of Legionella to cause disease, it's also its Achilles heel. Because Legionella injects a large number of these effector proteins, it also inadvertently injects other bacterial products, such as bacterial flagellin, nucleic acids, as well as bacterial cell wall components that are sensed by a variety of cytosolic sensors within the macrophage. And so these include members of the NOD-like receptor family, including NOD1 and NOD2, which sense bacterial peptidoglycan, the nucleic acid sensors, RIG-I and MDA5, as well as the inflammasome, which is a multi-protein signaling complex that assembles upon detection of bacterial LPS or flagellin and allows for the recruitment and activation of host cysteine proteases termed caspases that go on to cleave downstream substrates such as members of the IL-1 family of cytokines that are important for host defense. And these caspases also allow for the initiation of a form of cell death known as pyroptosis that allows for the elimination of this infected cell. Conversely, we know that Legionella does have some effectors in its arsenal that try to thwart the immune response. And so a good example of that is shown here. So Legionella has about a dozen effector proteins that potently inhibit host protein synthesis by directly interfering with ribosomal functions. And so our lab has been really interested over the past 10 years in understanding how a robust pulmonary immune response can be generated against pathogens such as Legionella. And so when you think about it, this is actually quite an important problem because we know that we live in the sea of microbes. So with there are greater than 1 million microbes per cubic meter of air, and each of us inhales more than 1,000 microbes with every breath. And furthermore, the surface area of the lungs is quite large. So if we were to unfurl our lungs, it'd be approximately the size of a tennis court, and we have more than 1,500 miles of airway within our lungs. What's remarkable is that we only have a very limited number of innate immune cells that defend the space, and it's estimated that there's only about 1 alveolar macrophage that are defending every 3 alveoli within our lung. And as I just told you, pathogens such as Legionella have just a unique ability to replicate within alveolar macrophages. And so how can we defend against Legionella? Particularly when Legionella, as I just told you, has all these effector proteins that can block host protein synthesis. And so when I started the lab 10 years ago, we became very interested in understanding this question. And so we knew that despite this blocking protein synthesis, that there was a very robust inflammatory response that ensued in response to infection with the production of large numbers of cytokines as well as chemokines. However, it was not clear to us whether these directly infected cells were the ones producing these cytokines or whether it could be neighboring bystander cells that are recruited to the site of infection and could be responding to infection instead. And so what we know now after many years of work, I'm just summarizing many publications from our lab, is that these infected alveolar macrophages are actually impaired in their ability to produce cytokines in response to infection because of this block in protein synthesis. However, we found that these macrophages are able to produce a select number of cytokines, including the inflammasome-dependent cytokines, IL-1 alpha and IL-1 beta. And these cytokines signal to IL-1 receptor expressed in our epithelial cells and instruct these cells to produce the host factor GM-CSF. We found recently in a paper that we just published in Cell Host and Microbe that GM-CSF then communicates with recruited immune cells, including monocytes and dendritic cells, and actually reprograms these cells to undergo aerobic glycolysis. And this metabolic reprogramming is critical for these cells to produce critical cytokines such as TNF and IL-12. IL-12 in particular then communicates with NK cells as well as other lymphocytes such as alpha beta and gamma delta T cells, and instructs these cells to produce the cytokine interferon gamma, which then acts back upon macrophages and turns on antimicrobial effector programs that allow for the restriction and clearance of bacterial infection. And so if you remember what I told you earlier in the talk, that there's a relatively small number of macrophages within the lung, we think that the system that we've uncovered is a potential mechanism that allows for the immune response to amplify signals from a relatively small number of macrophages in order to mount an effective inflammatory response that allows for control of immunoevasive pathogens such as Legionella. And with this now, we're really interested in a number of future questions that our lab actively investigating. So we're really interested in understanding how this metabolic reprogramming regulates immune cell function in the context of Legionella infection. What other immune functions are carried out by our epithelial cells, whether the signaling circuit functions in other infectious and non-infectious disease settings. And then, of course, we're really interested in understanding whether aspects of this circuit fail to function in individuals susceptible to Legionnaire's disease or other infections. And so with that, I just want to acknowledge my fantastic lab. So I'm really lucky to have a great group of scientists, postdoctoral fellows, graduate students, and undergraduates. We have a lot of really great collaborators, both here at Penn, as well as elsewhere. And I'd like to thank my funding and thank all of you for listening.
Thank you so much for a really terrific talk. It was, a wonderful context to put it, set it here in Philadelphia. As we know, that was the big outbreak, and your work has certainly taken us to the very cutting edge of understanding the interaction between these bacteria and the host. So we really appreciate it. We've decided that we're going to hold the questions until the end of all the talks. So I'm going to thank you again, and I'm going to introduce our next speaker, who is Dr. Michelle Kutzler. Okay, so Dr. Kutzler is Associate Professor of Medicine and Associate Professor of Microbiology and Immunology at the Drexel College of Medicine. She received her BS in Biology from Temple University and her PhD from the Lewis Katz School of Medicine at Temple University. Her postdoctoral training was at the University of Pennsylvania in the Gene Therapy and Vaccines Laboratory of Dr. David Weiner, who was a pioneer in DNA vaccines. Her research showed that addition of certain chemokines could enhance the mucosal immune response in monkeys to a DNA vaccine to prevent simian immunodeficiency virus, this in the setting of trying to find a good vaccine for human HIV. At Drexel, her laboratory has developed a DNA vaccine for Clostridium difficile, which is currently being pursued for commercialization. And she's a co-inventor on 7 patents pertaining to DNA vaccines. She's also been, this is not her laboratory work, but she's been an outstanding advisor to our Eastern Pennsylvania branch student chapter for the last several years, and she is currently our president-elect of our branch. She's going to talk to us today about Philadelphia's rich history in vaccine research and development from empirical approaches to advanced technologies. So, Dr. Kutzler.
Great. Thank you so much for that wonderful introduction. I'm so happy to be here. Having gone to school at Temple University as an undergraduate, and then followed that with attending Temple University Medical School for my PhD. Then I moved to Penn and now at Drexel. You know, Philadelphia truly is my home, and being a part of this branch I've grown up with the branch truly, and it's really a pleasure to be speaking with all of you today. I just want to pause and make sure that my slides are projecting and that you can hear me okay.
Yes.
Great. Thank you so much, Toby. Great. So today what I'll be talking about is Philadelphia's rich history in vaccine research and development. And I'd like to spend the next 15 minutes taking us through a very rapid history of this wonderful history of vaccine research and development in Philadelphia. And what's really interesting is how we've moved from the empirical approach to more advanced technologies. So if we begin thinking through Philadelphia and its historical pioneers, I always like to start with the saying from Dr. Stanley Plotkin, who was an instrumental physician scientist. He played a pivotal role in the discovery of vaccines against rubella virus while working at Wistar. And he once said that only those who have seen the beginning can understand things of the present. And he uses this statement to portray the history of vaccine development. And it's now over about 225 years since vaccinology was launched with Edward Jenner's observations of using cowpox to prevent smallpox. So historical vaccine approaches included mostly empirical approaches without, let's say, immunological rationale. However, they were successful and they were able to treat several infectious diseases that had high mortality rates. So successful early vaccines were largely due to elicitation of antibodies, and these were based on predictions from animal models, natural infections, and other studies, including some seroepidemiology. So as we begin to look at the next generation vaccine strategies for antigen development, we're now basing this on genetic engineering or systems biology or structural biology approaches. And this is really helping us to identify the protective immune responses. And it's really quite impressive when we look back at the role of scientists in Philadelphia that they have played in moving the field of vaccinology forward. And in particular, when I think about the Eastern Branch of Pennsylvania, it played a significant and important role as a professional society. And when I read through Jim Papard's book, it's so impressive of how many monthly meetings highlighted some of the pivotal times and pivotal work of scientists in vaccine development. And another observation is the collaboration between industry and academia. And it's very much highlighted when I take you through these vaccine stories. So Philadelphia was truly at the center of key discovery and technologies. So in the next 10, 15 minutes, I'm going to highlight some of this rich history in Philadelphia. So to start off with, vaccines have changed the world. And if you look in the pre-vaccine era on the left, morbidity in the United States was very high. And more recent reports of cases in the US on the right, post-vaccine licensure have significantly decreased. Vaccines truly have changed our world. And so I'd like to just think through, I usually in my mind break down vaccine strategies based on the early studies which really relied on empirical approaches. And so these past vaccine successes were largely due to just protective antibodies that were based on predictions, as I mentioned, around animal studies, natural infections. And so beginning with Edward Jenner with smallpox in the 1700s, through mid-1900s, a lot of these studies were based on those types of experiments. And I have highlighted some of the key discoveries and scientists that have did their work while in Philadelphia, and sometimes reporting them at our branch meetings. So, and then what I consider the next generation of vaccines include more advanced recombinant technologies. And so during this era, there was an explosion of new potential strategies based on genetic engineering, systems biology, and structural biology. And so some of these studies include the work of Robert Austrian, who I'm going to briefly mention, Maurice Hilleman, Hilary Kaprowski, also Irving Millman and Baruch Blumberg, and then later Fred Clark and Paul Offit. And importantly, the work being done in Philadelphia was always in collaboration with an academic unit, as well as companies, which include Fox Chase Cancer Center, Wyeth Litterly, Merck and Company, GSK, and Wistar. So I want to start off with Dr. Hilary Koprowski, and he was born in Poland in 1915 and received his medical degree from the University of Warsaw in 1939. Upon moving to the United States in 1944, he joined Letterly Laboratories, where he developed the first live oral polio vaccine to be used in clinical trials. He joined the Wistar Institute in 1957, became director of the institution, and under his direction at the Wistar, the rubella vaccine was developed, which is currently the rubella vaccine that's used in the combination vaccine. Koprowski himself was credited for developing the rabies vaccine, the one that is most widely used today, as well as the first effective vaccine against polio. Even though his polio vaccine was shown to be effective in Africa, it was never approved for use in the United States. Another big star in vaccine in Philadelphia was Dr. Stanley Plotkin, and he played a pivotal role in the discovery of a vaccine against rubella virus while working at the Wistar Institute in Philadelphia. He worked on other vaccines as well. Chief among them was also rabies, rotavirus, and the CMV vaccine. Interestingly, the vaccine for rubella is based upon the RA273 strain of the virus, which was released to the public in 1969. And this vaccine was what led to the eradication of disease in the US, according to the CDC in 2005. So Plotkin worked with Dr. Koprowski, and they worked together to produce the rabies vaccine during the 1960s and 70s. And as I'll talk about in the next couple slides, Plotkin also worked with Fred Clark and Paul Offit for the rotavirus vaccine. And in 2006, that vaccine became part of the US recommended vaccine schedule for babies. Another instrumental scientist in Philadelphia during the time of this booming vaccine era was Dr. Robert Austrian. He is responsible as the inventor for the adult version of the pneumococcal vaccine. And so he joined the faculty of the University of Pennsylvania in 1962, and he founded the Infectious Disease Fellowship there. It was during the 1970s that he oversaw trials of the pneumococcal vaccine in South Africa. And in that case, gold miners were particularly susceptible to pneumococcal infections because in the mines, there was very crowded conditions. And so they had exposure levels of different types of bacteria in their new surroundings. And so it was Austrian that really established this tremendous knowledge base of pneumococcal biology. So he analyzed 83 known types of pneumococci, and he determined 14 types were responsible for 80% of invasive pneumococcal infections, and that the outer coatings or capsules of these organisms is what should be included in an effective vaccine. So it was Austrian that devised this multivalent polysaccharide vaccine that played a major role in successful clinical trials that resulted in licensure. Dr. Baruch Blumberg and Dr. Irving Millman also played an important role, in particular in the identification of the antigen for hepatitis B, Australian originating in 1964. So the surface antigen led to identification of the complete hepatitis B virus and its role in causing acute cancer. So it was the discovery of the Australia antigen, which had an important effect or important pivotal point in the study of hepatitis B, because hepatitis B at that time couldn't be cultivated in a lab. So they could use the Australian antigen as a model of the virus as a whole, and that Australian antigen provided a source for the vaccine. He worked alongside Dr. Irving Millman at Fox Chase Cancer Center, and they, again, helped to figure out how to separate the virus from human blood, and they were able to render it inactivating it for a source of the vaccine. So Dr. Millman was also involved in vaccines for tuberculosis, pertussis, and rubella, and he developed a test for hepatitis B in blood. And this was given to me by Dr. Toby Eisenstein. This is a conference brochure from 1982 showing the symposium that back then it was the Clinical Microbiology Conference, the hepatitis B, the virus, disease, and the vaccine. So this conference was chaired by Dr. Eisenstein and included other longtime branch members, Carl Abramson, Joe Bartola, Ken Cundy, Mort Klein, Linda Miller, and Norm Willett. And at this Eastern branch of ASM, it's where they really talked about this discovery of the Australia antigen. And now we can look back knowing how important that presentation was in leading to the hepatitis vaccine that we have today. And that leads me to Dr. Maurice Hilleman, who worked with both Dr. Millman and Dr. Blumberg on the hepatitis B vaccine. He's also credited for developing vaccines for measles, mumps, rubella, chickenpox, Hep B, Hep A, meningococcus, pneumococcus, and Japanese encephalitis virus while he was at Merck. He's also been a pioneer for combination vaccines. He was first to show that influenza virus changes each year in such a way that previous immunization or infection with that previous season of flu is not enough to protect someone from getting the flu again. So when we add up all of the vaccines and lives saved from the vaccines that he's developed, I mean, he has saved about 8 million lives every year. So he is quite a historic figure and vaccinologist that especially, you know, we're very proud from Philadelphia, or his work being done in Philadelphia. An interesting story was Dr. Hilleman's daughter, Geraldine, had the mumps. He swabbed the back of her throat, weakened the swab virus in his lab to create the vaccine for mumps. And this picture on the bottom right here is Geraldine, his other daughter, who is receiving that mumps vaccine from Dr. Robert Weibel. Another really important contributor to Philadelphia vaccine science is both Dr. Fred Clark and Dr. Paul Offit in their development of the rotavirus vaccine. They were both at Children's Hospital of Philadelphia, Dr. Clark at Wistar, and they worked to use a strain of rotavirus originally isolated from cow, and they modified it in Dr. Clark's lab at the Wistar to include individual genes from human rotavirus strains. And so they were able to modify that virus in such a way to elicit a protective immune response in babies. And this vaccine prevents severe diarrhea and vomiting. It's common with this infection. And this work was given the gold medal, highest honor, which is awarded to those who have profound impact on the lives of children in the United States and worldwide. So switching gears now, when we think of moving from the earlier empirical approaches to more waves of new technologies for vaccine development, the figure on the left here allows us to think about where we began, which is the early trials, empirical approaches shown in the yellow circle. And as we begin moving with technology, first discovery of utilization of recombinant DNA, the ability to conjugate and glycoconjugate vaccines so that we can now have protective antibody against several bacterial strains. The use of reverse vaccinology, which can identify and target antigens that lead to protective immunity. And next generation technologies, which include new adjuvants, structural vaccinology, synthetic biology, again, DNA and RNA. And so all of these strategies have really allowed us to expand the types of targets that we're looking at to develop vaccines. And importantly, emerging infections, which are so important in providing vaccines for prevention or therapy, including AIDS, anthrax, avian influenza, cholera, dengue. But importantly, I've circled a particular virus, SARS, in particular SARS-CoV-2. And for the last 5 minutes of my talk, I would just like to talk a little bit about some exciting new technologies that are being developed for SARS-CoV-2 vaccines, in particular by scientists, academics, industries in Philadelphia. So the COVID-19 vaccine landscape, if you look at the vaccine pipeline, the global vaccine R&D effort in response to COVID-19 pandemic has been unprecedented in terms of scale and speed. And there's over 140 programs underway, over 125 preclinical, and then there are about 27 phase 1, 15 in phase 2, 9 phase 3, 5 that have been approved for limited use. And different vaccine types or platforms rely on different ways to deliver that antigen. And shown in the bottom right are the most common or 4 general types of vaccine platforms that are currently being tested in preclinical and clinical phases. That includes live attenuated viruses, nucleic acid, which includes both RNA and DNA, viral vectors, which can be non-replicating or replicating, and then the protein-based inactivated forms. So, no single vaccine platform will be enough, will be alone really to meet the global need for COVID vaccines. And so the goal really is to develop more than one type of vaccine that can be used on a global scale. And so this multi-pronged approach is absolutely critical to the success of COVID vaccines. And so I just want to highlight 2 of these platforms because there are several labs in Philadelphia excitingly working on these platforms. I just want to highlight them briefly. The first is viral vector COVID-19 vaccines. And the 3 most furthest along in the pipeline are shown here. It's the University of Oxford, AstraZeneca, Can Biologicals, and Merck. So all of these 3 platforms and many in preclinical trials use either a replicating viral vector or a non-replicating viral vector carrying the coronavirus spike gene. And so through delivery of these viral vectors, you're inducing a specific immune response to that spike gene. The other type of platform that's very far along in the clinical pipeline are nucleic acid-based vaccines. And so nucleic acid-based vaccines is when the nucleic acid, which can be a DNA or an RNA, encoding the spike gene, is inserted into human cells. And once it's inside human cells, it's transcribed and translated using host cellular machinery to induce an immune response to the specific coronavirus spike peptide. And so there are several vaccine candidates in the coronavirus vaccine pipeline, including Moderna, Inovio, which is a Bluebell, Pennsylvania-based company, Pfizer, and BioNTech. And then there are other laboratories, including ours at Drexel and other labs at Wistar that are also looking at some nucleic acid-based vaccines. So key steps to developing COVID vaccines are first to identify target antigens, optimizing that immunization route, defining what the correlation of immune protection is, testing animal models, scalability, since we're in Operation Warp Speed, we have to have 1 million doses ready to go. So we're looking at scalability, and along with that is building production facilities, what is your product profile, and then targeting the outbreak forecasting. And so deciding how to roll out the doses and who are the most at-risk populations that will need to receive the vaccine first. So with that, I would just like to end with some of the current research in our laboratory. Again, we're looking at a DNA vaccine that encodes spike protein. And this spike protein is encoded, taken up by host cells to process and present and express the spike protein in the draining lymph node to naive B and T cells where it induces immune responses. And in particular, our laboratory is very interested in looking at an immune adjuvant system that can improve T cell responses in the draining lymph node, thus helping to generate better B cell function, binding and neutralization. So with our DNA vaccine encoding the spike protein, we're mixing with an ADA adjuvant. And ADA stands for the adenosine deaminase 1. This is a molecule that is particularly important in helping to boost immune responses in the draining lymph node, focused on T follicular helper cells. And so our hypothesis is by co-immunizing with this ADA adjuvant, the ADA will be carried to the lymph node from transfected cells where it boosts the T follicular helper immune response, upregulating costimulatory molecules in the TFH, stimulating B cells to migrate to the draining lymph node where they can differentiate and isotype switch and make antibody isotype that can neutralize the virus. And importantly, in the work that we've begun to look at the ADA adjuvant, we're starting in the mouse model. We are vaccinating with our SARS-CoV-2 antigen, plus or minus this ADA adjuvant. And what we have found is that after one immunization, we are able to significantly improve the titers of the receptor binding domain at day 7 after immunization, day 14 after immunization, and then again at day 21 after immunization. So this tells us that ADA might give a antigen dose sparing effect. So if we can include an ADA adjuvant after one immunization, you could probably use less antigen, because after 2 immunizations, the antigen catches up. So the ADA effect is no longer there. ADA after one immunization does improve the viral neutralization as measured by pseudoviral neutralization assays. And again, after 2 immunizations, the ADA adjuvant's effect, the antigen catches up after 2. And we do want to develop a vaccine that's a rapid responder. So the goal is to be able to develop a vaccine that only needs 1 immunization. We also know that ADA adjuvant can help with improving the durability of the response. So by including that ADA adjuvant in the immunization, we have a significantly higher durability, day 50 post-immunization. And historically, coronavirus vaccines and coronavirus immunity is very short-lived. So the development of an adjuvant that can boost durability of the response is quite important. We also have data suggesting that ADA enhances memory B cells, and that's another very important factor when looking at vaccine formulation adjuvants. And it enhances the T follicular helper costimulatory molecules, which correlates with improved antibody responses. And then the last figure that I'd like to show is that we are very interested in testing whether ADA can improve immunity in aging mice. And the goal would be that this vaccine could potentially be used with a coronavirus vaccine, and particularly at-risk individuals, including elderly. So we use an aging mouse model where mice are either young or old. And we have data that in the aged mice, ADA improves over aged mice without adjuvant. And so there's a significant improvement in immunogenicity in the ADA mice that are old that have received ADA. So we're very pleased with these early data coming out, looking at ADA as a potential immune adjuvant in our COVID vaccine formulation. And with that, I'd just like to summarize by, these are things that we can talk about in our discussion, around what are the immune correlates for COVID vaccines, what are some of the expected results that we would like to see from vaccines. But I'd just like to end instead with this highlight of where we've come, Philadelphia's rich history in vaccine research. And I hope that I've given you a great sense of all the wonderful vaccine research that's come out of the city, and in particular, what we have to look forward to. And these are just captured of 3 institutions that are currently working on COVID vaccines. Dr. Schnell's lab from Thomas Jefferson. Thomas Jefferson is a very active branch member, Drexel, as well as Wistar. And so there is really a lot to look forward to continue with successes in vaccine development in Philadelphia. So with that, I'd like to end and let's get started so we can start talking and having a great conversation around all the talks today. So thank you so much.
Michelle, thank you very much for a very stimulating and interesting talk, and certainly for showing how rich the history of our branch is in terms of participating in vaccine development, and how many stellar, outstanding scientists we had who did that, and also collaborations with the pharmaceutical industry in the Delaware Valley. That was really great. I'm going to turn the microphone over back to Linda Miller, who will set the stage for how we're going to do the questions.
Okay, thanks Toby, and thanks Michelle, and thanks to all of our speakers. So I'm going to explain, we're going to have a Q&A session now. This will only work for those of you who are on the Zoom meeting. It won't work if you're on the YouTube link. To ask a question, you should be able to click on the participant box at the bottom of your screen. And when you do that, a little blue hand will come up. And then I should be able to see that you have raised your hand, and I will then call on people who have raised their hand. When I call on you, I'm going to ask that you say your name and where you're from and who your question is directed to. And I appreciate that. We'll also try, if we have time, if people want to write questions in the chat, you can also at the bottom, you'll see there's a chat and you could put a question in there, but it's kind of hard to see those. So I encourage you to raise your hand in the participant box. So I am going to, and I'm going to ask Vincent Tam to help me. I'm going to ask if people can maybe ask somebody to ask a question or somebody just to raise their hand, because looking the participant box that I can see on my screen, and I don't see any questions yet.
Somebody, Teresa Simon, raised her hand.
Oh, there we go. Okay, great. So Teresa, I should be able to unmute you and allow you to ask a question.
Okay, well, you wanted somebody to try to raise their hand, so I did. But I only have a comment. So I have been a member for forever, and I first started to come to Jefferson face to face. I think I got 2 in before COVID. I live in Toms River, New Jersey. So, but I, worked in a number of different hospitals in Philadelphia, and I've been a member for years. But the talks, this was fantastic, I have to say. I've thoroughly enjoyed every talk. And will the slides be available, or, I guess that's my only question.
Yes, the YouTube. There also will be a YouTube that will be available of the session. So that
we'll post the video
post
on the website as well.
Yeah,
we'll post a video on the website as well.
Yeah, what we've been doing, Vincent usually breaks up the meetings into segments that we can post on our website, and so we should be able to post each talk as a separate talk. If we break them up into, as opposed to one 4-hour session, we'll have all in one place. You can link on any particular talk. So that you should see that in the next couple of weeks.
Okay, well, fantastic. Thank you.
Thank you. All right. And I'm just looking to see if I have other. I'm going to ask a question while people are thinking. I actually had a question for Jim Poupard. Jim, you had mentioned that Ruth Miller was our first woman president and that she was fascinating. And I just wondered if you could share any other interesting thoughts on her.
Sure. Can you hear me?
Yes.
Jim Poupard.
Yes, we hear you.
Yeah, she was our first president. I implied that there was no prejudice there. It just, there was not many to choose from, because in those days, you really had to have a PhD to be a president because of to keep everybody happy. So she was active, very active in the branch. It was interesting, she got into microbiology because her father was a pharmacist. So that's why she went to the College of Pharmacy and Science, but then got sucked into microbiology. It was interesting that when you look through the branch meetings, especially when the national meetings were here, it was her job she always had the same post, and that was to figure out how to entertain the wives of the attendees and to have social events for teas and things like that. And it just showed you that she just took everything with an open mind. She was such a wonderful person. I've interviewed her several times. Some of the interviews are in the archives, and that she ended up at MCP for quite a while and lived a very long life to about 90 years old. I just think it ends up that, yes, we eventually fixed it by Toby Eisenstein was the second woman president, and Linda Miller was the third. So we have the first and the third as Miller, so that's easy to remember. And she was very friendly with Dr. Morton, and I think he inspired her to become very active in the branch, and she was active for about 25 years.
Great, thanks. I'm looking, I don't see any other hands raised. I have a couple. Oh, there we go.
Yeah, Stefan, did Stefan Peterson have his hand raised? No, went away. I thought I saw it. Guess not.
So I will ask another question. So Alan, you, great talk. And I'm one of the areas as another person who's a clinical microbiologist and spent time in the hospital and in industry. There's been a lot happening in antibiotic drug development. Well, there's been a lot happening because of the need for antibiotics, but there's has been a lot of issues about companies having to getting out of it. And I just wondered if you wanted to comment on that at all.
Yeah, that in the early 2000s, it was getting increasingly difficult to get new drugs passed through the FDA. They were very expensive to do clinical trials, and unfortunately, a lot of companies decided not to pursue that. They wanted to, it's profitable to have a patient on a drug such as a cardiovascular drug or diabetic drug where they're on it for life, and to have these short intervals where you have someone on an antimicrobial agent for 5, 7, 10 days, and then you're having to depend on acute infection. There had to be some type of an incentive. I think the IDSA played a major role in bringing attention to the fact that there are fewer and fewer antimicrobial agents being developed. And that's why we've seen a little bit of a bump up in the late 2018-19 period. But even so, even with the little bump up, as you saw in one of my slides, you know, we're at the stage from 2010 until the present, we're about where we were in the 1940s. So we just continue to need incentives for drug development. It's very expensive to develop an antibiotic. A lot of compounds are looked at, as you know, thousands are looked at, maybe one gets through development, and if you're lucky, that one may get through a safety profile and into a phase 2 or phase 3 trial. That's why there's so many companies, obviously, with the COVID vaccine too, because you have to have dozens of companies looking at potential targets and potential vaccines in order for one of them to succeed. I think because of the technology now in 2020, the vaccine companies are a little ahead of the curve, especially with the experience of some of the newer vaccines for Ebola and Zika and the experience more recently with that. So I don't know what the future holds. I know that there was a big push for MRSA, and it turned out that with good infection prevention and with fewer reimbursement, when CMS became involved and said, we're not going to reimburse you if you get a hospital-acquired MRSA infection, then there's a lot more emphasis on stewardship and infection prevention. So in spite of not having new antimicrobials, some of these major pathogens of concern are gradually decreasing, and with the time, you know, will tell if that curve stands up and if we continue to see a decrease. It's a challenge. There's no question. It's a real challenge for these larger companies to be able to move forward with, probably with government help, to be able to develop new compounds.
Yeah. Okay. Thank you. Thank you. I see a couple of questions on the chat, so I will see if I can.
The last question is from Cheney Lee. Michelle.
Okay.
Yeah, thank you. I can take that question. Thank you, Channy Lee, for that. The question is, how soon do you think we'll have a COVID vaccine? You know, this is a very important question. I'm sure all of us are wondering, you know, when that vaccine is going to be ready. And I think it's really important for all of us to appreciate that vaccine from bench to bedside, it's truly 15 years of development. And the fastest we've developed the vaccine, the fastest vaccine that has been moved to market was 5 years, and that was the Ebola vaccine by Merck. So what they are doing right now is this Operation Warp Speed, which is, I'm using that term just to, the way that they're being able to move that forward more quickly is they're doing concurrent processes. So usually the preclinical testing is done and then you move it to the clinical phase 1 and then it's moved to phase 2. But a lot of the processes are being done concurrently. So while they are moving it to phase 1 safety, they're doing preclinical animal testing to look for immune correlates, to look at also, they're building manufacturing facilities that that way they can get those 1 million doses ready and up and running. So they're trying to shorten that 5 years down to 12 months to 18 months. So having said that, they will not release a vaccine unless it is safe. So there are 2 trials that are in phase 2/3 safety. They're getting the vaccine in many people. So we will know by the end of the year, beginning of next year, the safety profile. So in my mind, I think it would be safe to bet that a safe vaccine would be available next year. They may release that vaccine early for healthcare workers, for people that are at risk, but I would say that it's going to take a full year from when they started. So I would anticipate in 2021.
Thank you. Thanks, Michelle. We have another question from Teresa Simon for Irv. In his talk, the slide with syphilis cases of 500,000 globally. Was this globally? And then the US population at the time was 130 million. Did I read the graph incorrectly?
Yeah, it was 500. This was in the United States. So that was a graph from the CDC from a 80s or 90s MMWR, and the total number of cases was in the United States. So it was 500,000 or 600,000 cases of syphilis total in the 40s and 50s, and then there was about 100,000 cases per year of primary syphilis in the U.S.
Okay. Thank you. Toby, did you have questions? I have another one for Irv, but I don't know if you had any questions for the group.
Sunny, would you like to just tell us a little bit more about some of your current work showing how the Legionella engages with the intracellular sensors and how that affects their ability to replicate intracellularly?
Yeah, sure, Toby, I'd be happy to. So one thing that's been a major interest in our lab is understanding how macrophages actually do control Legionella. And so as Toby knows from her own work, historically, actually, mice were not a good model system for Legionella infection. Many researchers, including Toby, actually had to use guinea pigs. And actually the CDC, as I mentioned, used guinea pigs in their initial research on Legionnaires' disease. And so it turns out actually that most mouse strains are actually highly resistant to Legionella, except for one strain called the A mouse strain, or it's referred to as AJ mice. And it turns out that AJ mice have been mapped to have a mutation in a gene called NATE5 that is an important gene now known to be involved in inflammasome activation. And so all other mouse strains have a wild type copy of this NATE5 gene that's important for inflammasome activation and killing of the macrophage. And so what's interesting actually is that whereas mice are restricted for Legionella infection, and so are mouse macrophages, human macrophages are actually highly permissive, even though humans actually do have a ortholog of mouse NATE5 called human NAPE. And so we actually are doing a lot of studies in our lab to understand how human NAPE is functioning in detection of Legionella and other bacterial pathogens. And so we actually have some really cool studies going on right now where we found recently that human NAPE actually can detect all the different bacterial ligands are normally sensed by the different mouse NAPes. So there's 5 mouse NAPE sensors. And so we're trying to figure out, if human NAPE is important in control of Legionella infection in humans.
Well, that's really interesting. I will add that Dr. Herman Friedman, who was a longtime member of our branch and the past president of our branch, pushed for years to adopt the mouse model. And he had so much trouble with study section, who said, no, mice are naturally resistant. And, you have to use guinea pigs, which turns out are extremely awkward to use as an experimental animal. For one thing, you can't catch them because they don't have a tail. And you have to work in an isolator because they're infected with Legionella. So I think he discovered that the AJ mouse was the one that was susceptible to Legionella.
Yeah, that's right. Yeah, so I actually was thinking about talking about that today, but I just didn't have time.
Yeah.
But yeah, I think since that initial discovery, there's been a lot of research now to really map this gene. So like the work of many labs across the world. And so for the mouse models, actually, some labs still use the AJ mouse, whereas other labs, including ours, now because we know that this NAPE5 gene recognizes bacterial flagellin, we can do a trick where we can knock out either genes in that immune sensing pathway, like NAPE5 or the downstream signaling proteins, or we can actually use Legionella that lack flagellin, and they're able to replicate to high numbers within Black 6 mice and replicate the disease we see in AJ mice.
That's very interesting. Thank you.
I see another question for Dr. Shin. I'm trying to get it. It says, it's from Chani Lee, and it says, with buildings being closed for months, what do you think should be done to limit possible Legionella infections when buildings do reopen?
Yeah, thanks, Chani, for that question. I think that's really important, and it's been definitely something that's been discussed by water control experts and been covered in the news recently. So, the number one most important, way of controlling Legionella infections in buildings is to, routinely flush the water supply. So, opening up taps, laying water flow through the building. And obviously in severe cases, when they do detect high amounts of Legionella, they do have to use stronger measures like, flushing high amounts of chlorine, or some water control experts have recommended heating the pipes to very high temperatures to try to kill off the bacteria. But I think the simplest is just to flush the water supplies routinely.
Interesting. Thank you. Vincent, I see you have your hand raised. Do I need to unmute you? There we go. You should be unmuted. Okay.
So this question is for Michelle. So it seems like we do pretty well coming up with vaccines to generate an antibody response. But when it comes to cell-mediated T-cell-based vaccines, we're pretty terrible, like making HIV or TB vaccines. Does the ADA adjuvant, other than helping the T follicular helper cells, can it alter the T-mediated response to pathogens?
Yeah, so that's a great question. So sorry about that. So yes, and so first the DNA antigen is able to trigger T cell responses. So the nice thing about the nucleic and the RNA vaccines is we know the antigen by itself does elicit some cell mediated immunity. And that's because that peptide is processed and presented in class 2 and class 1. So the S antigen alone, we do trigger some CD4 responses and some CD8. But the beauty of the ADA is that it's secreted by that the antigen presenting cell, which takes up that adjuvant. It binds to the CD26 on T cells, and so it's actually upregulating costimulatory molecules on T cells so that it's a better binder to the naive B cells in the germinal center. So you're right. It's the key, and we think this is going to be very important for for COVID immunity, is not just having a neutralizing antibody response, but to truly get at that durability, boosting that initial pool of cell-mediated immunity. And so the nucleic acid vaccines, which are furthest along in the pipeline, tend to trigger that T cell response. And in addition, we think ADA is going to bring another level of that cell-mediated immunity through that TFH function. So thanks for that question.
I have a question actually for Irv, and I wondered, Irv, you did a really nice job talking about the history of diagnostics, and I just wondered if you would comment a little bit on how these newer rapid diagnostic tests that we have, both for bacteria identification and even for susceptibility testing, are changing clinical microbiology labs, and how clinical microbiology labs function and interact with the clinicians.
There we go. That's a really good question. So I was just talking to somebody earlier today about this. Rapid diagnostics, particularly for say identifying bacteria in blood cultures, for example. So the rapid blood culture ID systems and the susceptibilities that go along with that. Some of the technology is pretty expensive, and institutions, I think, what's emerged over the last few years is, this field called antibiotic stewardship. And, when you look at the studies on the impact of some of these rapid tests on antibiotic prescribing, either, narrowing antibiotic therapy or de-escalating antibiotics, depending on what their results are. Institutions are still trying to figure out the circle of communication between the lab, infectious disease specialists, the pharmacy, on getting those results in a fashion that somebody can actually act on it. And some institutions have done a better job than others in figuring out how to do that. So I think we're still in the early stages of seeing kind of these, I would say ultra rapid results that are ready within a couple of hours after, you start to see some growth in a culture. And we're not there yet because of these really the need to change the way medicine is really practiced in hospitals, as opposed to rounding on a particular schedule and kind of batch actions. It's got to really get to a more kind of immediate response. And so these are still some of the major gaps. It's not the technology is there, and it'll probably be improved, and hopefully the price will become a little bit more affordable. But I don't think it's the technology that's actually the bottleneck there. It's really more of the practice and implementing. What do you do with all these rapid results? And this is not a new topic. I mean, rapid identification and susceptibility has been around for decades. And, we talked about this, 20 years ago. I was like, okay, well, we can get a result in 3 or 4 hours or 5 hours. What difference does it make? And we're still asking those questions.
Yep. Thank you. Are there any other questions? Anyone from the committee or Toby?
So can I follow up on that a little bit?
Sure.
So with multi-drug resistance as a dangerous threat, the idea of phage therapy keeps coming up. From a diagnostic point of view, is it really feasible to really quickly identify the correct strain and then come up with a phage that can kind of curb the infection and kind of stay on top of that by identifying this rapid phage resistance as more like a personalized medicine?
I'm not really all that familiar with the technology to do that. My kind of very simple understanding of using phage to specific phage to identify a strain. I'm not sure that the technology is there for for routine clinical use. But maybe somebody else in the audience knows a little bit more about that.
I'll just make a comment. I know that CARB-X is this organization that is funding both antibiotic drug development and rapid diagnostics. And phage has come up a number of times as something, certainly lots of people are looking at it. But this hurdle, very close to what Irv said, first of all, can you come up with a test that's simple, quick, cheap, and then use it and implement it in a way that's effective in the hospital? And exactly what Irv said, sometimes the biggest challenge is kind of changing the way medicine is practiced. And perhaps for very serious infections, for limited numbers of patients, that's doable. But now you just took away the financial incentive for a company if the drug is only going to be used in very limited ways and only when there's a companion diagnostic that goes with it. But it's a big challenge, but I know people are looking at it.
But I kind of if you think about the CAR T cell story, and institutions have they're collecting the cells from specific patients and then farming them out to industry to then modify them, produce them for the specific tumor type, and then deliver them back to the patient. And that's of course, those are cell cultures. It takes a long time. It's a very complicated process, but you can see a parallel with phages in terms of identifying a specific phage that will knock out this multi-drug resistant organism, and then you got to produce it in quantity that's safe to deliver back to a patient. I don't know that the technology in any clinical lab can do that. It sounds like we'd have to partner with some pharmaceutical companies to rapidly produce that. And since it's not cell culture, it's maybe it could be done a lot quicker.
Yep.
Yeah, I'd like to also mention that the microbiome has a lot of phages in it, and then you'd have to look at the interaction between a new phage being introduced therapeutically and what effect that has on your normal flora in the intestinal tract, where you see lots of bacteriophages and phages and that type of interaction. So I think the safety profile is going to have to be very carefully looked at.
Thank you.
A question in the chat for Irv. Or how do the rapid susceptibility results compare to conventional susceptibility testing? And if you have results of the rapid test, will conventional susceptibility testing be needed?
For the systems that have rapid testing, they've performed pretty well compared to reference susceptibility testing. Matter of fact, they couldn't be approved unless they met certain criteria for kind of correlation with reference methods in terms of major error, very major and major errors. So the ones that are marketed now, do pretty well. But they're, like I said, they're very expensive, and institutions have to figure out is there a value in having something that costs 100 times more than what they can do it in the laboratory, and what are the downstream economic value to will they be able to get more specific therapy to their patient faster? Will that mean fewer, less days of being in the hospital, less mortality, better outcomes? And so the kind of the economics really comes into play in how institutions make decisions on using that. Will it replace conventional testing? Well, conventional testing isn't, all that slow. So I'm not so sure that, conventional testing is going away anytime soon.
Yeah.
Would you agree, Linda?
I would agree. I think, especially when you think of lower middle income countries and, you think on a global basis, and it's hard to beat that, those tests. I think there's a place. And, I hate to be, not futuristic thinking, but I think that cheap, rapid, easy to use diagnostic that can then be utilized by physicians and impact patients has got some more hurdles to overcome. I have a question, a historical question for kind of Jim and Toby, but I wondered if there's any other comments or questions. Okay. So Jim, you mentioned kind of the clinical microbiology and the branch and the split and then getting back together and, kind of the academic clinical microbiology, basic science, clinical microbiology, some tensions that it sounds like there were. And yet, having joined the branch kind of pretty soon after that happened, but after that happened, I went into this happy kumbaya, super active branch. It was after they had come back together. And I just wondered if you guys, in these times that we're in now of kind of competing groups, wondering if you have any thoughts on how did the branch do that? How did what sounded like a lot of a little bit of stress got, kind of really well?
Yeah, I think, Jim, you should answer that.
Yeah, well, a lot of it comes down to money. And as I mentioned, we had royalties on the books, we had royalties on the kit, and the charges. In other words, before the clinical section, everything was the monthly meetings. That was it. And as the numbers of clinical people grew, they got more and more dissatisfied with the normal meetings. So that's what precipitated it. They said there was too much immunology, too much biochemistry, not enough clinical. So the solution was, yeah, do that. I think the attitude was, it's an experiment, try it. That's why we'll have Monday nights clinical and Tuesday nights a regular meeting and see what happens. Well, it was pretty apparent what happened. And it seems so crude to us now. We're talking about a symposium. We're talking about some of the things they did were so innovative. It wasn't, you couldn't go into the internet and get this information. So we became a really big source of information and training, particularly for the bench tech, that our symposium was really, more sophisticated and then designed. Look, let's put the focus on the bench tech because they're our lifeblood. And again, when you looked at who attended the meetings, it was the clinical people, a lot of them the technologists. But then as the new regulations came out and first of all, clinical labs weren't making as much money anymore. And luckily the clinical group had a significant amount of money from royalties. And they were technically the branch royalties, but that steering group controlled it. So essentially it was to them. And I don't think anybody could have predicted that that group could have been so successful so quickly.
Just kind of, moving forward, this has been the history of the branch is the branch has adapted to kind of the changing patterns of the people, the interests, the institutions, and it's really reflected in all the content that the branch delivers. And it's so nice to see the branches thriving. We're seeing many more of the graduate students involved, from faculty from the different institutions. And while we have, and we have a, I wouldn't say it's, it's a perfectly balanced branch. You can't balance everything, but we have something for different interests. For microbiologists in the Philadelphia region. And, a lot of branches outside of us, differentiated to just one kind of area of focus. And they remain that today. And there's nothing wrong with that. It reflects kind of the local environment. So I think, we have a lot to be proud of in terms of how we've kind of kept all these different topics of interest, and being able to learn from basic scientists and the clinical microbiologists, and all that content available to everybody for very low cost. So it's a major accomplishment.
Great.
Just to
Thank
follow,
you.
just to follow up on that. Yeah, it's the innovation was significant. I think if you look at the different periods, what period are we going through now? Like the clinical people had their vein. They were the dominant group for quite a while. Now, I think we really do rely on the student chapters, because that gives us a direction. And we don't identify it as education, but the one thing that started us as such a strong branch was with 5 medical schools. Education had to be important. And that's the one thing that took us all the way through, that we call it the symposium committee, and we call it the education committees over here. But it all boils down to education. We've been educating microbiologists for 100 years. And so far we've been lucky in getting it right.
Good note to end on.
Yep, that was great. So I am going to then take this opportunity to once again thank all of the speakers. They were wonderful. Thanks to the committee who put this together, and Jim Poupard, thanks for being the instigator to make this happen. And Dieter, thank you as our current president, and Michelle, looking forward to you for the future. So thanks everyone, and take care. Appreciate all your help. Okay, bye.
Bye.
Congratulations, everybody.
Thanks.
Bye.